Okay, well, welcome to the November meeting, and as usual before we start we'll go through some of the things in the last month. For starters, we'll start with the sound of the Big Bang. So this is the first 760,000 years from time zero up to 760,000 years condensed down into about a minute and a half, 2 minutes. And the frequency is actually increased by a 26 orders of magnitude for you to be able to hear this, because the wavelengths were of the order of the length of the universe. So really, really low frequency. And the only reason you can hear it is because of that. So I thank Eden White for that one, pointing me to that link. That was a very interesting link that he came up with. While that's going through, down in the bottom right hand corner we have a video from Greg Walton. I'll just turn the Big Bang down a little bit, of an aurora from up in the Little Desert in Victoria. It was actually brighter down here, and some spectacular photographs taken from Aspendale foreshore that I saw, but unfortunately I couldn't get one of them to show you. Lots of really rich colours was seen down there, but they had a very good view, as you can see there, up in the Little Desert, which is sort of the eastern side of Victoria, about halfway up, I think, from memory. Over on the right hand side we also have the NASA Lucy mission, flew by asteroid Dinkinesh, number 152,830. And they were very, very surprised there to see not only did it have one satellite, but it had a pair of satellites that were in contact with each other. So you'll see in the square that is labelled B, how you see the two smaller satellites is a contact binary, where just very weak gravity is holding those together as it flew by. So that was a chance encounter. As it is, the name Dinkinesh is Ethiopian for wonderful, and is also incidentally the name that they call in Ethiopia the Lucy hominid fossil. You know, the very famous one was called Dinkinesh, and incidentally that's why NASA called its mission Lucy as well, because of the similarity to the hominid fossil. And lastly on there, goes for a couple of minutes, is NASA visited the Pilbara back in August. As part of searching for life with the current Perseverance mission. They've recently extended, unfortunately, the deadline.
Everybody to the Pilbara. We're delighted to be able to take you into a site containing the oldest, most convincing evidence for life on Earth. In rocks that are 3.5 billion years old. It's a great opportunity to come and see what you might be looking for on Mars.
We can see rippled sediment, beautiful ripples here, continuing along, and it comes up to the edge and it pinches out against the side of the stromatolite and then continues over here on the other side. Beautiful ripples.
So what we're looking at here in Western Australia are what are known as stromatolites. These are rock features that were precipitated or caused to precipitate by mats of microorganisms that were living at the time, again 3.5 billion years ago.
So a stromatolite is a physical feature. Usually it's either a dome or a cone-shaped feature, and these are formed when single-celled organisms living together in a colony either trap and bind sediment or precipitate sediment on them, and then these photosynthetic organisms grow up, and so you see these layers that repeat in that shape. Sometimes they branch, sometimes they grow, sometimes they shrink, but what it is evidence of a colony of life from the earliest evolution of life, the earliest fossils that we have.
And these organisms then had their presence here on Earth captured and preserved in the rock record for all of this time. And so what we're looking for are these particular structures that these microorganisms made that are distinct from what geology normally does.
So the greatest thing about Australia is that it has some of the oldest rocks and some of the best preserved rocks for all different time periods in Earth's history.
And it's important for us to come here because what we're looking for here is the oldest convincing evidence of life on Earth. And in our search for evidence of life on other planets beyond Earth, especially Mars, it's important to understand how difficult it is to convince people of what we're seeing here on Earth as being evidence of life from 3.5 billion years ago. And if we're looking for something similar on Mars, it's a much more challenging prospect.
So in order for us to find a biosignature, there are actually 5 stages that have to happen, and all of them have to happen and in this particular order. The first is life has to exist. The second is life has to create some kind of a fossil that we can recognize and we can see as unique enough to be indicative that there was something going on there. Third, that fossil has to be preserved immediately or very soon after it's formed. The fourth step is that preservation has to continue for a long period of time. And then finally, we have to find it. So it either has to be eroded or it has to be somewhere where we can look at a rock and recognize that there's a fossil. That is an extremely unique and difficult process to have happen. So there's only a fraction of life that ever existed ever becomes a fossil. It's in fact an incredibly lucky process to go from life living at some point to a fossil that you can find.
And so that's why building that story takes a lot of time and why it's difficult that any one particular feature may not be biological. But when you combine all of these things together, that is what convinces people that what we're actually looking at is evidence of 3.5 billion-year-old life on this planet. So trying to do this here on Earth is difficult enough, and then trying to do it from 100 million miles away with rovers that have cameras and you have to send signals that take a really long time to go back and forth, even more challenging.
Earth and Mars may have had similar pasts, and the more we learn about Earth's past, the more we may be able to apply it to Mars. Now that we're collecting samples at Mars, wouldn't it be unbelievable if we were able to find something that indicated similar things that we're finding here on Earth that indicate, hey, there may have been life in the distant past on Mars.
And announced today was the fact that the American senators just cut by 2/3 the budget for bringing those samples back from Mars that Perseverance has been dutifully leaving up there. So the timeline is going to slow very, very considerably. Obviously, they have monetary worries elsewhere in the US. Okay, well, with tonight's meeting, we'll begin with 1 minute silence, and I'll ask you all to be upstanding for 1 minute for one of our long-term members, past president for well over a decade, Peter Norman, who passed away about a week or so ago. Okay, if you take your seats, thank you. Right, so welcome to November's meeting, which is the last monthly meeting held during the year. Since we last met, new members include Alec and Marilyn Clues, Tony and Nellie Nightingale, who've rejoined after coming back from Queensland, and Abhinav Gajarel. Are any of those here tonight? Well, welcome to the Society. If you have any questions as you go along, feel free to say hello to any member of committee who will now put their hand in the air so that you can look around and pick the one who's less scary to actually approach. They are a scary looking bunch, but they're not really. As usual, we'll go through the events of the past month and what's coming up. I'll look very quickly at some of the Ig Nobel Prizes. If any of you are familiar with that from past years. Chris will then do the AstroMoPho, and Guido will have a double song and dance with Sky for the Month and JPL. Back to back, okay, Guido? Sure. Yep. Then we won't actually have Eden tonight because he's away unwell tonight, so we'll be skipping over that and put the theory of everything off until he's feeling a bit better. Then Dave Rolfe is back from the US and promises a very interesting talk about his experiences there. Then we'll look at the NASA Psyche Mission in some depth from the actual principal investigator of the Psyche Mission. But this lecture was actually given before the launch, so it may be that we have some more updated information coming from Dave's talk there. And on the assumption that we have enough time towards the end, we'll look in a bit more about the European Space Agency's Gravity mission that was shown a couple of months ago in the meeting. I had a couple of questions that this particular clip will answer. If for some reason we can't cover it tonight in this meeting, it'll be online for looking at the meeting on YouTube. And then at the end we'll close with showing where the Earth is in its orbit around the Milky Way and what the Gaia mission showed about that. Okay, so recent events. The photo taken here is by Nerida in the background, where we had two French visitors here at the Briars, shown on the right-hand side, the two standing next to me over on the far right. And they gave a talk actually that evening as well. Alas, it was completely clouded for them, so they never got to see the Southern Hemisphere either in Sydney when they first arrived or here. It was their first time outside of the Northern Hemisphere as well, so they'd never seen the southern sky. And fortunately, after leaving here, they went off to Central Australia to go on a bit of a driving trip to Goss's Bluff and Uluru, so hopefully they got to see something of a clear night sky there, which would be unusual if they didn't. A couple of days later, we visited the school associated with Alex Cherney, Stella Maris, and they had a wonderful night as well, and the clouds were very kind. Mentone Primary then had a Year 2 sleepover, and we had some very good feedback shown down in the bottom right-hand side by the coordinating teacher there, who was really impressed by the Year 2s, and I have to say they were quite a lively bunch for those that turned up. Lots of energy at that age. Then we had the Scouts, Cubs and Guides night on the Friday. Again, clouds were very kind. And the public night at the Briars was overall about 90% cloud, but those who stayed around actually got to see clear conditions. It was only the pessimists that left at 9:30 didn't see very much, whereas those that stayed around till 10 o'clock were greeted by very good views. And the cosmology meeting was held at the Briars as well. So coming up on the horizon, we've got this Saturday working bee. We think it will be starting at 4 p.m. if we've got someone to open up on the day. Committee meeting is next Tuesday for those interested. Then we have the major VASTROC conference, the Victorian Astronomy Convention, here at the Briars the Saturday after, on the 25th of November. So as things stand at the moment, that's fully booked and has been for a week or so. So if you haven't got tickets to that, you'll need to go and beg with one of our committee members, and maybe we will, if you're a member, we'll be able to squeeze you in somehow. We've got the public stargazing night at the Briars with Trevor on the 1st of December, first Friday of the month, and that's fully booked. The Christmas Star concert, we've currently got 23 booked for that on the 8th of December, which is a Friday night. Then we've got a private family here at the Briars with disabled children on the Saturday. And the big Christmas dinner, we've only got 31 booked so far, which is then on the 16th of December this year. So if you're interested in coming to the Christmas dinner, do book online and see one of the committee members if you're new to the society. Then in January, we've got 4 stargazing nights, first Friday and Saturday, and then a couple of the Fridays afterwards, and those have already started filling up. And those who aren't aware yet, down in the bottom right-hand side, we've got the almanac that shows you what's in the night sky. Currently available. You could buy one here tonight if you like, because members get that pretty much at cost price. Whereas I think it's $25, whereas the recommended retail price is $32.50. Right, well, I'll begin with a couple of minutes on the Ig Nobel Prizes. Now, what the Ig Nobel Prizes are is a light-hearted opposite view of the Nobel Prizes that are awarded each year for scientific excellence. And they honour scientific achievements that first make people laugh and then make them think. And they're actually presented
The winner is from the
Nobel
UK
laureates.
and Poland. The Chemistry and Geology Prize is awarded to Jan Zalasowicz for explaining why many scientists like to lick rocks. The prize will be presented by Nobel laureate Rich Roberts.
Well, really is a great pleasure to be able to give you this prize. I have to admit, I'm a chemist by training, but I never learned to lick rocks. Congratulations.
Thank you very much indeed. It's a great pleasure to have this prize and you know, for such a fundamental thing indeed in geology and chemistry as licking rocks, you know, which geologists do all the time in the field, because something that's not very clear then becomes much clearer when you look at it with a wet surface. And so I'm a field geologist. I've licked 1 million rocks. But 200 years ago, geologists were licking rocks to find out what they were, with no machines, no textbooks, no microscopes, no chemistry, indeed. They did geology, at least in part, by taste. And it worked for them.
I'm going to give you something they never got to have. It comes along with the prize. Here is your $10 trillion bill.
Oh, that's super. Thank you. Yes, that's riches indeed. Yes, there's something to be cherished and spent all at once, or not? There's the question.
Do you happen to have any other tasty rocks with you?
Tasty rocks. Yes. This one is from it's Wales. It's a trilobite, relative of crabs and lobsters. Again, about 400 million years old.
Would you do the honors for us?
Licking the rock. Yes, that will be. It's a mud rock. You can't see very much like this, but when you lick it, you can just begin to see grains of silt and the shape they are and how they're arranged and so on. Of course, if it's a rainy day, you don't need to do that. You know, so quite often in the field in Wales, there are days when you don't have to lick rocks, but on dry days, that's the standard, repertoire.
Well, we know from you that geologists like to lick rocks. Rich started out as a chemist.
Yes.
I wonder, do chemists in general like to lick rocks?
I started as a chemist, and no.
You never acquired the taste.
I never acquired the taste. I never found one that tasted good.
Meet Giovanni Arduino. He was a much more cheerful man than he looks here. And he didn't mind getting his boots dirty. He became a geologist, even before such a thing really existed. A challenging handwriting, but this interpretation of his local Italian mountains is the evolutionary beginning of the modern geological timescale. How did he tell the rocks and minerals apart, though, with no fancy machines to help him? Well, his letters show that he used all his senses, including developing a taste for rocks. Ashes from a shelly mudstone, he said, taste like fire and leave a certain sweetness and a skinned tongue. And the mineral marcasite had an acid, spicy flavour like the acidity of wine. it was a kind of mineral taxonomy of taste, an ancestor of geochemistry. Giovanni Arduino reminds us how to do science from scratch. One suspects, therefore, that he must have liked cats.
And that's a genuine prize. So the $10 trillion note is a real thing, and not 10 trillion of our dollars, it's 10 trillion Zimbabwean dollars. And with that, I'll throw over to Chris for AstroMoPho.
All right, welcome to AstroMoPho number 10, our monthly astrophotography challenge. And challenge number 10 was Spooky Astro, thanks to it being Halloween last month. And Peter Wiley suggested we do spooky objects in the sky. So that was what we were tasked with capturing. And to start off, we've got this 3-panel mosaic by Ig Nobel of the Tarantula Nebula and part of the LMC. This is captured with his FRA 300 scope, 294 camera, and Acier and Optolong L Ultimate. So the Acier lets you do mosaics and plan mosaics in the its Stellarium programs features. So you can plan different panels mosaics, and then it'll move the mount and the camera to the different sections of the sky for you to get the different panels. So this is a work in progress for Nick, and he's actually got another 3 panels coming onto that as well to capture part of the LMC just to the top of the screen there as well. So keep an eye out for that on the social medias. He'll be posting that up when he's done. Next we've got, well, I'll go through who actually did the challenge this time. It was Nick Axaris, of course, Kelly Clitheroe, Guido Tack, Greg Walton, David Rolfe, and myself all managed to catch spooky objects. And we've got this one here of the Andromeda Galaxy by Guido Tack. 40 to 180 second frames, so a fair bit of time on that. And the reason that this is scary is because when it collides with us, we'll all be dead. So that'll happen in about 4 billion years or so, I think. It'll end up merging with the Milky Way. Andromeda is actually quite large, so it's around about 3 degrees by 1 degree. And when you consider that the moon is only about half a degree, is that right? Half a degree circle? It's actually a fair bit larger than the moon. And when we were down at the star party, you can sort of, if you look carefully, you can actually just sort of make it out with the naked eye. And it was quite low on the horizon, but yeah, even through a pair of binoculars, it looks pretty spectacular. Also in the photo, there's M110, which is the galaxy on the bottom there, and M32, which is the small galaxy on the top. Not sure what that was. But there are satellite galaxies of the Andromeda Galaxy as well. And looking at the sky chart, looking to the northern horizon, it's actually pretty low in the sky, so you can see where it is when it's at its highest altitude there. It is still only about 20 degrees high. So yeah, it does stay pretty low in the sky. Oh, actually less than that, 10 degrees. Yeah, 10 degrees at its highest point. So it is fairly low on the horizon, and that's from here in Melbourne. Next we've got a couple of tarantulas, so some scary spiders captured by Kelly from the Geelong Astronomical Society and one from David Rolfe, so a couple of different fields of view. Kelly's is a 107mm telescope, so much more zoomed in, and David's with your 71? William Optic 71? Yep, and also monochrome and colour camera there from Kelly, a monochrome one from Dave, and what was it, just red, blood red and luminance, so pretty scary. We all know where the tarantula is, so I didn't bother putting that sky chart up. It's a new feature, the sky charts, by the way, if you hadn't noticed. Then we've got a coven of witch heads. Is it a coven? Do you need 4 witches for a coven? I think it's, anyway, there's a few witch heads there. Myself, Kelly and David all managed to get shots of the Witch Head Nebula, which is just off this bright star Rigel, which is one of Orion's feet. So mine and Dave's were captured from the Vic South Star Party. Kelly's was captured from her backyard, I think. I put a bit of green on mine to make it extra spooky, but yeah, so the Witch Head's a reflection nebula. So it's not actually emitting, it's reflecting light from the stars around it. And looking at where it is, if we've got Orion there and we can see Rigel up the top, the Witch Head is just above Rigel if you're ever looking for it in the sky. And it is fairly faint, it's not a bright nebula, so it does need a bit of exposure to capture it, and it's not really something you can see naked eye either. Then also we managed to capture part of the Veil Nebula from Vic South, and these are objects that we don't really manage to see from here because they are fairly low on the northern horizon, and we can't really see them through trying to look through Melbourne's sky pollution. But when you've got a clear northern horizon, you really do get a view of some of these beautiful objects. So the first one up there is the Veil Nebula by me. It's also called the Witch's Broom, and the bright star there, which I think is 51 Cygnus or 51 Cygni, yep, that represents the witch riding the broom on the broomstick there. So nice spooky one there. And the other one next to it is NGC 6992, which is the Eastern Veil Nebula. So the Witch's Broom is on the west side of the Veil Nebula. The Eastern Veil is on the eastern side of the nebula, and I reckon that there looks like the xenomorph from Alien. So that's why I reckon that's scary. So yeah, but that one there is actually only 30-second exposure shot. So 20 seconds, because I meant to take 120 seconds, but I missed the one. So it's still got 10 by 20 seconds and came up pretty good. We've also got the Eye of Sauron Nebula, which we're renaming now, by Guido, and a starless version of that to make that extra scary. So if you're ever looking towards the north, now the Eastern Veil, the Veil Nebula is actually a supernova remnant left over from a exploded star. And if you're ever looking north, it is up at, this one's up at about 20 degrees altitude at its highest when it's due north. And apparently it is also visible through binoculars, although I didn't try to spot it through a scope, but it is quite a bright nebula. So you saw even my 20-second shots managed to get a pretty good image of it. And this one here is the Helix Nebula, the Eye of Sauron Nebula. So that's just in Aquarius, or near Aquarius, and it's still pretty close to Saturn, has been for a few months now, so it's still able to be seen and able to be imaged. And that Helix Nebula, looking at it through Greg's scope at the Vic South, was pretty spectacular. You're looking at it from a dark side through a nice big aperture telescope, and it just fills the eyepiece. It's a really nice view. Thanks, Greg. Here we've got a video of some satellite wars, which Greg captured, so we should be able to see. And you can see there's some sort of space battle going on there. So they're all satellites streaking through the image there. Looks like you've got the same ones over and over again, but they're all different, are they, Greg?
They're all different. I can explain why this happens if you want me to.
Yeah, by all means.
So if you've got the Earth up here, we'll grow with Earth down. This here, you can imagine the atmosphere goes right around the Earth, and the sun in the night is only clipping the top of the atmosphere. So only those satellites there are being illuminated. Only the ones at the very top are illuminated. That's how this happens, because all the others are in the shadow. So the sun is round behind you. It happened right at midnight. That's when it was at its brightest. So the sun was behind the Earth, and the only bit of atmosphere that was illuminated. And in the summer months, that the sun is higher to the South Pole, higher to the South Pole down here. So that's how that happens.
Thanks.
That's why you only see them at that point. There you go. You know now how it happened.
Thank you. Next one. This is also the Witch's Broom by David Rolfe. So they've got a fair bit of data on this. So now of HA plus 5 single 5 minute frame, or 3 single 5 minute frames of RGB. And getting images of this, we were only able to image it soon after sunset as well. So the sky hadn't completely darkened, which was a bit of a challenge, but still able to get some pretty nice photos there of it. So it is a fairly bright object, and we've got some really nice detail there too. That's all of the images that we had for this challenge. The next challenge we've got the Christmas star. So it's a Christmas theme. We're looking to get images of nice bright stars, and we've got some of the brightest stars in the sky at the moment with Sirius and Rigel and Betelgeuse and Echina. Alpha Centauri is not really good for imaging at the moment. It's fairly low on the horizon unless you're willing to stay up pretty late. Comets as well, Christmassy sort of themed Christmas stars. There's also the Angel Nebula and the Christmas tree cluster as well that you might be able to try to capture. The Angel Nebula is fairly faint, but it's just off Orion there. It's part of the, what's the next constellation down? Anyway, that's where it is. You can see in the middle of the screen there, just off Orion's belt. And the Christmas tree cluster, which also has the Cone Nebula in it, is also just pretty close to Orion as well, if you're interested in having a look at or imaging that as well. So the Christmas tree cluster you can actually see in a telescope too, I believe. So something to have a look at. Okay, any questions? Nope. Very good. Thank you.
So this is November, December, and maybe a little bit of January because we don't have a meeting in December. Let's see. So first of all, look at the solar system. So at the moment you can see this is the inner solar system. So Earth is here. Mars is pretty much on the other side of the sun. So we're not going to see that at all at the moment. And then Venus and Mercury on either side of the sun right now. So if we actually let this run a bit faster than real speed, then we'll see that within the next month, obviously, Mercury and Venus move a bit like that. Mars doesn't move that much compared to us, so it'll still be very much behind the sun for the next month and January as well. And you can see how Mercury now basically moves to the other side because it's a lot faster than we are in its orbit. If we zoom out a bit, we can see the outer planets, and they're all still really nicely visible in the night sky. So Jupiter and Saturn are both past opposition now. Past opposition now. Yes, so they are both still nicely high in the sky. Saturn is moving a bit into the western evening sky. So you'll have to. Well, it won't be there for the whole night, but it's still really nicely visible at the moment. And yeah, Jupiter is just a little bit past opposition, so still very high and bright in the sky. Let's have a look at the sky for the 1st of December and looking at the planets. The first one is Saturn, right? So that's first one is Mercury, of course. So Mercury is an evening object on the 1st of December. So the greatest elongation, 21 degrees east, will happen on the 4th of December when it will reach magnitude minus 0.5. So pretty bright and also pretty large, 6 arcsecond disk. And then it will move into inferior conjunction on the 23rd of December when it will be lost in the glare of the sun and between us and the sun. So moving away from Mercury. All right, now we're looking at Saturn. So Saturn still quite high in the evening sky. So I think we're probably moving ahead a bit to about 10 p.m. now. You can see Saturn there in Aquarius at the moment, still quite high and yeah, nicely observable at the moment. It will be the brightest object in the evening sky in the west. still at around 16 arc seconds apparent size and magnitude, roughly magnitude 1. So slightly dimmer than at opposition, but certainly still observable, good for, well, we don't have any school nights or things like that coming up, but hopefully for some of our members' events. The next one after Saturn, I think, is Neptune, which is in a similar part of the sky at the moment, up there. But Neptune, pretty faint at the moment. Magnitude 8 and a pretty small disk, so visible through a telescope, but obviously not very impressive. So it's currently in retrograde motion, and then that retrograde motion will end in early December, and then it'll start moving like normal planets again in the way you would expect across the sky. All right, so if we fast forward a bit towards midnight on the 1st of December, I think, maybe we'll just move over to Jupiter straight away. This is around 11 p.m. now. Jupiter pretty much in the north there. So Jupiter is now past opposition, as we saw earlier, but it's still very, very bright and very, very large. So the disk is still about 46 arc seconds and magnitude minus 2.7, so clearly the brightest object in the sky. And it will be near the moon towards the end of this month on the 25th of November, and then again on the 22nd of December. Not very close, so you wouldn't probably be able to get a nice photo through a telescope of both the moon and Jupiter, but it will probably look quite nice in the sky at that time. And I think the final one of our giant planets, Uranus, is also in a similar part of the sky as Jupiter at the moment. So I think we'll just move over a little bit. And that is actually just past opposition, so that was yesterday. And it's now magnitude 5.6. So if you're lucky on a dark night with no moon, you might be able to see it as a naked eye object, and certainly through binoculars or a telescope. All right, so on the 1st of December, I think we have to wait a bit longer for the moon to appear. So I think it's going to be around 2 p.m. or so. There's the moon there in the middle. So let's have a look at the moon phases or the major events for November, December. So the next full moon will be, so we're just past the new moon. The next full moon will be on the 27th of November. Then we'll have the new moon on the 13th of December, another full moon on the 27th, just after Christmas, and then the new moon on the 11th of January. So we should have some reasonably dark public nights in January, actually, around that time. And finally, towards, or just before sunrise, we can have a look at Venus, which will be in the early morning sky. So this is around 5 a.m. now. And Venus is clearly a morning object at the moment, and by far the brightest thing in the morning sky, with magnitude minus 4 on the 2nd of December. Christmas star, Venus, yes. One more option there, that's right. So that's a comparison of the apparent sizes around the 1st of December. Well, Mars is on this one. I didn't put Mars on the other one because it's just behind the sun at the moment, so nothing to see there. All right, a couple of comets in the sky. There's more than these, but I think most of them are pretty faint, like less than magnitude 14. What happened now? Magnitude 14 or something like that. Are we back? Yes. Okay, so the first one, comet 103P Hartley 2, rising just after twilight, but it's fading from magnitude 11 to 13, so it's already a bit faint. Then comet 2P Encke setting shortly after sunset, so probably also not a very interesting object to observe. I'm not sure how to pronounce the next one. Let's say 62P. that one seems to be a bit more interesting. Christmas star. So perihelion, so the closest approach to the sun on Christmas Day. And it's in Leo at the moment and possibly brightening up to magnitude 7. So we'll see what happens. And it will be close to the galaxies in Leo M65 and M66 in mid-December. So that could also be a really nice imaging opportunity. But Leo is not that high in the sky and towards the north. So we'll have to see whether we can do anything from here, but at least might be an interesting opportunity. Pan-star, so S3 Pan-stars rises around midnight in Centaurus. And it's possibly brightening up to magnitude 7 early in 2024, but yeah, we'll have to see what happens with that one. A couple of meteor showers. So we've got the Geminids coming up in December, and they are usually quite nice to watch. So there's lots of them around. They're a bit better like positioned in the sky from the northern hemisphere, but at least we will be able to get to see them, and they're around the new moon, or not too long after the new moon. So there shouldn't be any moon in the sky when the peak happens around December 14th, 15th. The other two were listed in the almanac. I'm not sure. I don't know anything about them. They seem to be a bit more erratic. So some years they might be interesting, and other years there's basically nothing to see. All right, just a quick look at the sky on the 1st of December towards the south. So the small Magellanic Cloud is now really high up in the sky around or just after sunset, and you can see Sirius up there and Canopus really dominating in the sky again. So clear sign that we're in summer now, and of course we have towards the morning, then in the early morning hours, that part of the Milky Way is coming up high enough again to observe, but of course that's pretty low in the sky at the moment towards the south. Looking towards the northern horizon, we can clearly see Orion now rising at a reasonable time. So again, clear sign that we're heading into summer. And in terms of, you can see Jupiter there dominating in the northern sky. And other than that, the kinds of objects there, I'm not sure where's Leo just rising there around 2 a.m. So that would be where you could find that comet hopefully in mid-December. And I think that is all for Sky for the month for the next couple of months. And the sources were Stellarium, NASA, Eyes on the Solar System, and the Astronomy 2023 Almanac. Any questions? And we've got, of course, the solstice coming up. I mean, I didn't have the Earth on the on the list there, but yeah, we've got the solstice coming up. I think on the 22nd of December, technically this year. Any questions? All right. Okay, so my next thing I wanted to talk about tonight is my visit to JPL. I visited JPL actually twice this year in August and October. And Peter mentioned that it was for work. It was actually for work, but it also was a lot of fun. It was a great visit. So just a bit of background, JPL, the Jet Propulsion Lab, is one of the main NASA centers in the US. So it's a research and development center, and it is close to Los Angeles in Pasadena in California. It was actually founded in 1936, so well before NASA was founded. So it's one of the oldest research centers as well. And it's managed by Caltech, by the California Institute of Technology, which is an interesting kind of arrangement, and it also makes the center a bit more open than maybe some of the other NASA centers because it's attached to a university. And the main goal is to design, build, and operate robotic spacecraft. So that's really important. They mostly focus on the robotic missions, right? So they don't do a lot of, for example, Earth observing satellites. They don't do a lot of manned missions, although they support some of those. It's mostly focused on these big robotic exploration missions. And they also operate the Deep Space Network, including the tracking station near Canberra in Tidbinbilla. So the reason I went there was, you might recognize the background there. So this is the reason I was able to go, because my colleague, Professor Chris Lawrence from Monash Uni, is running this National Indigenous Space Academy program, where 5 Indigenous students from STEM disciplines had an opportunity to go to NASA for a 10-week internship. And so we started that whole program with like a space boot camp at Monash, including a visit here to the club and some stargazing, which was really nice. And then the next day, all of us together flew out to JPL and then spent a week there. Well, they spent 10 weeks there. I spent a week there with them, and then was able to go back a few weeks ago to visit them again. And they're all doing really interesting projects, quite a diverse range of projects in all of the different areas that JPL works in. So one of them is working in robotics, one is working in kind of software design for stuff that is used on the International Space Station. One did work on kind of how microbes grow on spacecraft. One did work on hydrothermal vents, so the underwater kind of hot vents where we believe maybe life started on Earth. And the last one is working on, I think, vacuum chambers and kind of operating them more efficiently. So really a diverse range of projects from kind of science, engineering, computer science, and so on. So we all went to JPL. This is part of the main JPL campus, the main building there. It really looks like any kind of university campus. It doesn't look very impressive. They've got a massive NASA sign, of course, but other than that, it looks like any normal university campus from the kind of 70s and 80s maybe. Although the roads have nice names like Surveyor Road and Mariner Road and so on, and the buildings have signs like Flight Project Center and stuff like that. So it's an absolutely amazing place, because everywhere you go, they're doing really absolutely state-of-the-art, high-tech stuff, both research and actual development, engineering, and operations. This is one of the signs at the kind of entrance of the campus. So it's all of the missions that are currently in flight that are managed or operated by JPL. So we see a lot of missions around in Earth orbit. We see Voyager 1 and 2 out there, in very deep space outside the solar system, the James Webb Space Telescope, Juno around Jupiter, and then of course a lot of missions on and around Mars. So that's kind of part of what they do there. This is a really cool area on campus, basically, which is called the Mars Yard. So that's just an outdoor area where they basically simulate the ground conditions on Mars, and where they just drive around with the rovers to make sure that they behave the way they should on this kind of terrain, right? So they've got some kind of steeper terrain with some rocks there and some kind of sandy areas and so on, so they can really simulate how the rovers would react when they drive over these different types of terrain. And the actual rovers are in the shed here in the background. I'll show you some images from inside in a minute. And kind of on the other side of this, they have these rock samples. So these are not samples from Mars, but they are samples from Earth. That would be amazing if we had that much material from Mars, maybe one day. These are all samples from Earth. I think some of them including from Australia, because they're collecting all kinds of different rock samples to simulate the kind of conditions that the rovers would then encounter on Mars. So for example, if you look at the two rocks here, and I've got a bigger version of that, they're actually testing the drills that are on the rovers on these samples to make sure that they don't just destroy the drills or just pulverize the rocks or whatever. So for example, you can see these round holes here. So that's where they use kind of an abrasion drill to kind of just scrape away the surface, where the surface has been affected by kind of, I guess, weather and radiation and so on, to get to the lower levels. And then they use instruments to analyze what exactly that rock is, whether that is really one where they want to take a sample. And then they drill into the same kind of rock with another type of drill that they've got attached to the arm, where they can actually take a sample from the rock. And then they store the samples in little canisters and hopefully bring them back someday if they don't run out of money before then. But that's the plan. So the Mars Sample Return Mission is one of the big things that JPL is working on. So that's one of their main goals at the moment, to actually bring the samples back that the rovers are, the one rover is collecting at the moment. This is the door of the lab where they have all the rock samples. It's quite a funny place. Okay, so now look inside the shed where they store the actual rover. So these are actual engineering models. They're basically identical to the things that are on Mars at the moment, which is absolutely amazing to get that close to these things. The only difference is that they don't have the nuclear batteries at the back. So they just have a long tether coming out the back, because they obviously don't have to power them with those sorts of batteries. But other than that, they're basically identical. This is, let me think. I think this might be the Perseverance model. Yeah, I think this is the Perseverance model, so the newer of the two big rovers. And I can have a quick look around that one. Yeah, so the reason I'm pretty sure it's Perseverance is because it's not as dirty as the other one. So if we look at the other one, that has a lot more, I'm not sure if I can, I don't think I can easily zoom in here, but it has a lot more dirt and dust and so on, because they actually use these and try out different things. So for example, they try out how to deposit the sample containers on the surface, because if they have to drop them out of the belly basically onto the surface, because they want to leave some samples on the surface to collect later. And so they had to try out what happens when they drop these samples. So they just dropped a bunch of samples again and again and again on different types of ground and so on. This is actually not the one that's taking the samples, right? Because this is the older version, Curiosity. And Curiosity has different tires or wheels, as you can see, right? There's this kind of pattern on the wheels. If we go back to the previous one, this one has a different pattern on the wheels. So this is the more modern version. So this is one of the wheels, and I'm not sure if you can see it, but this one looks pretty bad. So this looks like it's close to falling apart, and apparently this is better than the ones that are actually on Mars, because they have to go over lots of really sharp rocks and so on all the time, and the rovers are heavy, like they weigh, I don't know, 1.5 tons or something like that. And these are just, I think, pretty much solid aluminum wheels. And these ones are basically destroyed. Apparently the newer ones on Perseverance are much more durable, much more robust. So that was just amazing to be able to actually just pick up one of these wheels and have a really close look and so on. You can also see there's this kind of Morse code pattern on those wheels, which makes kind of imprints on in the sand, which is quite fun.
What's that, about 10 kilos?
No, this one was super light. It's less than 10 kilos. Yeah.
Do they still use them to lab up scenarios on Earth that they can then use to guide mission parameters and tasks on Mars?
Yes. So, for example, for the sample return mission, they use the actual engineering model on Earth to drop samples and then see whether they kind of hit the wheels or kind of fall into the path where they want to drive and things like that. So they still use these to also, I think at some point, I'm not sure if that's right. I think they, for example, they were carrying around rocks in the wheels for many kilometers. Just something got stuck there, and I think they can try out kind of maneuvers they could use to maybe get rid of these things and stuff like that. So they, like anything that might be a bit dangerous or a bit experimental, they can try out with basically an identical model first. Of course, the conditions are not identical, right? Because, I mean, gravity is, of course, a bit more of a problem here than it is on Mars and so on. But anyway, it seems to be still an active thing they're doing. This Mars yard is also used for, so not just for the 2 rovers, but also for new developments that they're now working on for other missions. This is mission control. So they have a mission control center there, where this is basically just the communications center where basically all the data comes in from the deep space network and then gets distributed to the actual missions. So this is not where they're controlling the rovers, for example, right? This is just where they're talking to them, right? So all of the, for example, the plan for the next day needs to get uploaded. So the plan gets sent to mission control, and the mission control makes sure that it gets uploaded to the rover, and at the same time that all the data from that day gets downloaded and so on. So the actual mission control center for the rovers looks like this. So it's basically office space, no windows to the outside actually. They operate in shifts that are synchronized with the Martian day, not Earth day. So that shifts by half an hour every day. So especially in the beginning, they were actually on 24.5 hour or 25 hour, whatever the Martian day is, kind of time frame. So their sleep rhythm would kind of cycle through that over the course of half a year or so, which is interesting. They're not doing that at the moment, I think. And they've got basically a split between the downlink team that receives data, analyzes it, makes sure that everything is going well, and then an uplink team that prepares the new plan for the next day and then sends that off. I thought this one was funny, where this is an actual image from the rover hanging on the tethers from this sky crane spacecraft or rocket, and there's a little guy with a fishing rod there. Anyway. Also, they're very fond of their Lego models there as well. So they've got they actually had a couple of boxes there with signatures from lots of team members, which was, I couldn't get one unfortunately. They also, of course, the Ingenuity helicopter is also part of that mission. So they're also planning the flights for the helicopter and really planning ahead now that they've basically got a proof of concept that this actually works. They're planning for the next few missions and to see what they could actually do with these helicopters in the future. It was really cool to be able to talk to some of the engineers who work on these projects. And so, for example, the helicopter, because it's basically a technology demo, it's not, it wasn't mission critical for the success of the actual rover mission. On the one hand, they didn't have to use only highly certified components, and on the other hand, they didn't have the budget to use highly certified components, so they used off-the-shelf hardware. For example, the computer in the helicopter is based on something you would have in your smartphone, whereas the rovers are based on much more kind of safe and redundant and so on stuff. But the effect of that is that the compute power in the helicopter is more than than all of the JPL missions combined that they've ever launched, including the rover, right? Just because of this difference in like really mission critical, highly robust and secure stuff, and then something that they just tried out, which may have not worked at all, right? They weren't sure whether this would even survive the launch and the radiation and all of that, and it did survive that really well. Okay, so the same day I got to see the spacecraft assembly facility where they actually put together the spacecraft just before launch. So this is this is an amazing space. So it's basically a massive clean room where they really do the final assembly before it then gets shipped off to the rocket and then sent into space. And what's currently in there is the Europa Clipper mission. So that's the mission that's going out to Jupiter in October next year. It's going to orbit Jupiter and then make lots of flybys of its moon, Europa. And yeah, so you can actually see it there in the background. So this is an image a bit closer up. And the way they work there is really interesting. So they've always got a couple of people in the white kind of hats working on the actual systems and putting them together, and then someone with the blue cap just basically supervising and observing and taking notes. And so that's their kind of quality assurance process. And it's really interesting to see, because I mean, obviously they can't afford to make any mistakes here, right? Because it's yeah, absolutely disastrous if anything goes wrong here. They've also got that guy there, which is a mannequin that's always there. That's High Bay Bob, apparently. I think they put him there because whenever they get public groups coming through, they just want to have someone there as a kind of reference to see how big this space actually is. So they just put a mannequin there and put, apparently it's a supervisor with a blue cap. I don't know. The other thing, the final thing I wanted to show you is the von Karman Auditorium and the museum. So that's part of the more or less kind of public area. I mean, you can't just walk in, but it's kind of more accessible. So von Karman, I mean, some of you may have heard of the von Karman line. So that's basically like 100 kilometers up, so where space begins. So that's named after him, and he was one of the founders actually of JPL. And so this big auditorium is named in his honor. And you can see, I think this is Juno. Yeah, this is Juno, so a replica of the Juno spacecraft, and then a replica of the Voyager spacecraft there. And then just a big auditorium at a stage where they do public lectures, and also, for example, the launch that Dave is going to talk about more later, all of the team was assembled here and watched the launch from here. And that's Cassini, so the mission that went to Saturn. Well, it's not, I mean, it's a replica, and I think this is just a quarter size or something like that. They've got a replica of the golden disc on Voyager, which is really fun to see. Then the museum next door, they have models of, I think this is the Spirit or Opportunity kind of rovers from Mars, and Sojourner, the little one. I think that must have been one of the first rovers on Mars. And it's a pity that they don't have that one next. They've also got a big Curiosity model in a different building. So it would be really fun to see them side by side, because it's just at least 4 times the size of the Spirit, probably more. It's very, very impressive. And this is Galileo. This is the photo isn't very good, but it's massive. So they've got a replica of that one in the museum as well. And then all kinds of other exhibits and so on. On a little Hubble. I mean, that one was actually quite small, the model. And then an actual moon rock, which of course was really nice to see. But what I found even more interesting was this bit here, which is a piece of metal that they took off the Surveyor 3 probe that actually landed on the moon, and then Apollo 12 landed a few hundred meters next to it, and they walked over and basically brought some bits back to Earth for analysis, and now that's in the museum there. So that's actually really cool, that this is something that was on the moon, and then years later they went there and brought it back, and now it's in the museum there. So yeah, overall, there's so much more to see there. I could have just stayed there. It's a really fantastic place. It's obviously a really nice place to work as well. So anyone, all the people there were extremely welcoming, extremely kind of open, willing to share the things they were allowed to share. There's a big distinction between the kind of research projects that they have, which are very kind of open and international and so on, and then the more operational side of things, which is really limited to Americans pretty much. So they make a very clear distinction between those parts. But still, it's an amazing place to visit. If you're ever in the area, I would definitely recommend a visit. It's absolutely worth it. They do free public tours that are like 2 or 3 hours, so very detailed. You get to see a lot of these different places. Maybe you can't go into all of the areas, so I'm not sure whether you would get to see the rover models, for example, on a public tour, but a lot of the other places there. I'm not sure did this video play earlier? So that's a really fun installation where they have these poles with big signs on them, and the signs change, like the signage changes depending on what it's currently pointing at. So you can it turns around and points at different things in the sky and tells you where things are. So that, yeah, Voyager 2 was that way at that point. And I thought maybe I have to talk to Greg, maybe we can put something out here. I think that would be really cool. Anyway, that's all for me. Thanks. Any questions? Sorry? The first time I went, we had a COVID case in our group, and then we had a hurricane in LA. So we lost a lot of time. And we were there in a week where they didn't work on the Friday. And so I only had 3 days. And I decided that wasn't enough. And I had I had a week in October where I didn't have anything else to do, so I decided to go back. And my visa was still valid, so I decided to spend some more time there. The first one was work. The second one was part work and part for me, yes. Any other questions?
All right, so I also went to America, but not for work purposes, just for purely social. I like going to some concerts, so I went over to this Power Trip concert, and which was in California, and decided to make a stretch trip of either side of the concert. So started off Atomic Museum in Vegas. We flew straight to Vegas. I went there about 10 or 12 years ago. It's now been bought out by the Smithsonian Institute. It is a really cool place to visit if you're into lots of things. It's just amazing, well presented. We'll get there. One of the things I got into, they got pictures of the bomb and all the other stuff there, but they've also got a lot of stuff to do with the early experiments with, particularly, this got my interest, the space flight. So they were a Project Rover mission was done in the 1960s, where they were trying to do interplanetary rockets. So they were building these rockets to generate a lot of thrust, so they could go out to Mars and beyond and so on, with a lot of force, so you can accelerate away with lots of power and brake as well to get there to reduce the time. And it was all put to bed many years later, because apparently NASA had an issue where they weren't supposed to play with nuclear reactors in space, and there's also bad publicity. But interestingly enough, you can see there the thrust. I had a thing there. So Psyche, which was just launched, had a little iron engine, and it had 611 pounds of thrust. And you compare that to what we can get with these Phobos reactors and so on in space, where you're talking 250 pounds of thrust. So the rockets here, for the nuclear rockets, were, for the weight versus thrust, were just miles ahead. And that's quite interesting. There was a model there of the rockets. I want to actually do an article for Greg and put some more detail in, because it's very hard to show on the screen here. But half the display was about stuff that was going into space and orbit and so on, more so than the actual bomb itself. Draco has just announced it's being built now. It's made by DARPA and Lockheed Martin. This was only in the last year. They're actually gone back to start to redevelop space rockets under the Space Force banner. Because I still believe, from what I'm told, NASA are not allowed to do nuclear in space at this point. But I actually did notice when I was doing some research just last night, just making sure, looking for some more photos, I see ANSTO in Australia have also got a web page about it too now. I don't know what they're actually going to be doing with it, but they're referencing this exact mission. So maybe they're consulting. So after Vegas, we went to Palm Springs, where we had the big concert, and they got a Palm Springs air museum there, and it's actually amazing. And one of my favourite aircraft, the F-117, which I swear was only a fairly new aircraft, was there on display. So they're actually already becoming museum pieces. And with the cost of these things, I couldn't believe. And they actually said that they were the first museum to actually get a retired 117. So that was pretty exciting, watching the stealth, looking at the stealth plane. Yeah, so then after then we flew right across the country to the Kennedy Space Center. Leading right up to the trip, we booked a, kept looking at the Spaceflight Now website, and there was no flight, there was going to be no launches at all while I was there the whole week. It was going to be a complete disaster, but we'd already booked the tickets, 8 months earlier. Rocked up there, and we had a VIP tour, which actually drives you right around the launch pads up to 39A and B, where they did the Apollos and all that sort of stuff. Those pads, and we actually got to drive out to beyond the public areas on this tour. They do it one day a week on a Wednesday apparently, and drove past the shed from Boeing there of the X-37B, which is pretty exciting, and being launched next week on a SpaceX rocket. So the mysterious plane that sort of flies around for 2 years and lands. It looks a bit like a miniature shuttle. Some other things I saw at Kennedy was the SpaceX capsule there. You come back from demo mission 2. That's the actual real capsule, and they got some mock-ups of the booster there and the fins that do the guiding as they re-land. Went out to pad 39A and 39B on the tour, as you can see there, and that's actually Psyche sitting there on the pad. I've got some better photos in a minute, ready to go. So it was only 2 days before launch when we were there, and they actually said it's very rare. They don't normally let the bus trips go out when they're ready to launch at that close stage. Normally the security's clamped down, so the driver assured us we were special. And once you get past that security barrier, there's just stuff lying around everywhere. It's worth a fortune. There's a SpaceX capsule there, the Dragon capsule, ready to go on, just sitting under a tent, just randomly in a paddock. Probably worth, $1 billion. Yeah, in what's out there. So yeah, the bus trip went around, and that's the Falcon Heavy that we went to see, which was actually lucky because it was scrubbed a week earlier and actually come into the week we were there. So you can see there that's got the two boosters on the outside of the rocket, and that's Psyche sitting on top of it up there. A couple of different angles of it there. Couldn't get the logo, it was on the side that wasn't visible. Went past where they're building that Starship platform. That's got the big arms that kind of catch the Starship, and I think that's attempting to launch also in 2 weeks, another launch of that. You go past the big shed, the vertical assembly building. Apparently that's the largest single story building in the world. It's amazing watching that, and then the driveway from that shed all the way out to the pads where they used to take out the Saturn V's and so on. So while we're there waiting, there's a fantastic display if you ever get a chance of the shuttle. Atlantis is there. You can get up and look at it from below and above, and can't peek in the windows. You can't quite, they've made it so you can't quite touch it. But they got mock-ups there, and they got the actual capsules and cabins and the toilet and all the other bits and pieces. You can have a look around the walls. It's absolutely amazing the way they presented it. A replica there of the Hubble, and down further down near where we're sitting on the edge of the lake, where you look across to the launch. They've got another building there, which is the Saturn V building, and it's just, photos don't do it justice how big that really is. It's absolutely incredible. So we got there one day on a Wednesday, and Psyche was scheduled to go off on the Thursday. So we bought tickets. You got to buy tickets to go back, and if you want to go out and watch it at the the platform where all the TV shows the launches from. So we bought a ticket for the next day, and at midnight they scrubbed the launch for the next day, which was on the Thursday. So we decided we'd just go to Disneyland for the day, and then I had to buy tickets again for the Friday, because they don't refund or move your ticket if it's a scrub. It's just bad luck. You lost your money. Well, no, airlines would actually postpone your ticket. No, you got to buy it again, a completely new ticket. So that's disappointing. So sitting there in the morning, it was scheduled to launch about just before 10 o'clock, and we had to get there at 5 a.m. You have to get there so early to go on the buses through the security and out to the area where we are, which is near the Saturn V shed. It was so hot and so muggy in the morning. I'm thinking, how did they launch in this? It's just, the air was so thick, and there was all these people with these massive cameras and stuff. And I'm looking at their shots in the viewfinder, and they're horrible. The air was just so thick. Everything was bubbling, and it was it was in the low 30s, but just incredibly muggy. Yeah. So we went there. There was a guy there that works for NASA. He was giving a commentary there, and they plug you into the live feed. That board you saw on the last slide with the countdown, there used to be another board like that you used to see out in front of you. That broke down about a year or so ago, but no one's bought a new one because those two pads there are rented by SpaceX now, and they don't really care. They're not there for the public. So NASA used to invite people, but now it's those two pads hide out to SpaceX for the next 30 years. NASA use another pad, and the rest of it's now Space Force, which is all behind locked gates. So standing behind the guy who was telling everyone about the mission, and didn't realise, but there's an alligator just cruising through. So you couldn't get out closer there because it's guarded by gators. So I was sitting there watching it. Didn't want to look away from, so I'm holding the phone blind.
9, 8, 7, 6, 5, 4, 3, 2, 1.
They did warn us there was a 5-second delay between the countdown and real life. But listen when the sound starts. This is interesting. You can actually feel the heat hitting you, even though we're like 3.5 kilometres away. Fingers trying to stop it. Yeah, so that was pretty cool, but it was, I reckon, the landing was spectacular too, because the two outside boosters, oh, it's very hard to see, isn't it, a loop? It was hard to see, it was so glary. You can see there in the shot there, the two boosters come down, one was well ahead of the other, and you can see it's been burning for a bit and slowing up, and you can see the full thrust on the second booster. It's just to the side of it, so it's just starting to slow down. And we couldn't actually see them touch the ground though. The trouble was they landed right down on landing pads 2 and 3, which is inside Space Force's pads, but it was actually behind that big building, the vertical assembly building. So directly from our view, behind that is where they touched down. And that was a video SpaceX put up of the landings. I'm sure you've all seen these before.
I don't know, Daryl, but that sonic boom was great for us. I'm sure Jim is excited over there. There's the second one.
So they both come back.
I'm sure the host desk over there is feeling that really well.
Some interesting things. We actually heard 4 sonic booms. Yep. The rocket's so large
broke the sound barrier.
And we just heard booster landing confirmed, as we see on the screen. Both landing zone 1 and 2. Everything looks great. And then the call out for
Stage 2 FTS is safe.
Eco 1. Stage 2 engine cutoff.
Stop that now. All right. But what was interesting was it was actually 4 distinct booms, sonic booms, because the rocket was so long, the front edge and the back edge both break the sound barrier at different times. You actually heard boom, boom, and then a few seconds later, boom, boom, when the second rocket was breaking the barrier. So, as I said, it was 4 distinct booms. Now, the outside 2 rockets, they both landed, but they actually sacrificed the middle one because they built one there especially for them. It was going to be sacrificed because they needed the extra fuel to get Psyche further into its trajectory. So the middle one actually was never returned. It just crashed in the ocean a few hours later. So they didn't bother fitting it up. They were saying with the fins, and they got a cheap version which is disposable. Those 2 boosters that landed, I think there was 10th and 12th landing of those boosters, so they certainly get recycled. The one in the middle that they sacrificed, obviously, that was a virginal rocket.
I think the 2 boosters are already scheduled for another NASA launch next year.
Yeah. Yeah, and that was the first Falcon Heavy that, the 6th Falcon Heavy launch they've done. It was actually the first interplanetary mission that NASA's hired SpaceX to launch for them. So it was pretty cool to see that, and unexpected. So yeah, they're getting up there. And back to that talking about before, I watched a doco the other night. Elon Musk was talking about the interplanetary rocket nuclear thing, and saying that he's actually wants to try and help bring that technology on too, but I'm not too sure if they're going to let civilians companies play with it. So, but it's certainly amazing when you go out there how reliable these rockets are. I mean, it's almost routine now watching them go up. They got a tremendous record. So if you go there, you got to allow yourself a week and just keep your eye out each day when they're launching. I think we're just under 4 kilometres, so it's 3.8, which is, straight across the lake. There was another launch that night too, so I could have gone back. There was a Falcon 9 being launched with another set of his Sky Annoying internet satellites being launched that night, which Starlink. So, to send up 2 a day, it's getting pretty incredible how quickly they're launching them. I took the land out with me, so I think it was about $100 to get out there, and it also cost me about $100 in the Uber fare to get from Orlando out to Kennedy. So that's why I'm glad they scrapped the other one the night before I left, so I could cancel Uber in time. But Ubers are fantastic in America. I'd never used them before. I still lost $100, yeah, because you got to buy entry into the Kennedy Space Center, and then you got to buy another $50 or $60 for entry out to the Banana. What do we call it now? Lake Banana, something like that. That's the name of the viewing area there. So yeah, it's about $200. But I figured you're only there once, and you've spent so much time getting over there, you can't miss it. I actually thought we were all having bets whether they're going to scratch it beforehand due to high humidity. Well, as I said, SpaceX are doing these. They're not concerned about people paying money for that. There's a separate entity selling tickets to watch them. As I said, the launch where that display broke down, they have no interest in fixing it. They don't care. They just want to get paid to launch people's satellites. That's not there. They said they'll scratch it operationally, more so for the public disappointment.
Was it loud enough that you could feel the noise? Because I've heard when the Apollo missions took off from members, members a long time ago that went, but they could actually feel it.
You can feel it rumbling, yeah, and you can feel the heat, and the noise came about at the same time. So it was delayed. So you saw the smoke the steam coming off the chute, because they were shooting. You probably saw in the video it went off to the left through those ducts. And actually, when we drove back on the bus, there was a lady there from the who looks after, because it's actually a national park, that whole area, like a wildlife park. And they're talking about they actually scare the birds and all that sort of stuff away when they're about to launch. Because early on they used to have a lot of dead animals and birds because of the noise and the pressure of the launch, so they actually actively scare them away and stop them nesting anywhere near the launch. There was lots of cameras and that set up too when we went for the bus tour. There was a massive amount of cameras scattered everywhere, all these photographers and space reporters. Obviously we're not supposed to, you couldn't be left alone there because you'd steal a lot of dollars worth of cameras. But it's just amazing to watch the organisation there. All right, I think that's me.
Any other questions? So is SpaceX still the only ones reusing boosters?
Virgin are supposed to be reusing theirs. But aren't they going to do one in next year, and then they're going to have a year off, aren't they? Then they're coming back with a new one, I read on the forum the other day. So they'll reuse theirs. Well, they launch from the plane, don't they? So they... Yeah, that's right. They're only just the sky tourism. There's a massive new building right at the gate as you come in. Blue Origin are building a massive shed there just on the boundary. So I think that's Bezos's operation. So they're obviously setting up there as well. It makes so much sense. Alrighty. Oh, it was hard to gauge because, as I said, you can't stand right up next to it. It's smaller, I believe, physically. The new one, the Atlas. Oh, Starship would be the biggest of the lot, but I think the new one they're going to Artemis.
A couple of very interesting talks there, and good to have members over there and seeing some of these things. Very, very interesting. And by good coincidence, we'll have the main video, which goes for about 55 minutes, I think, all about the Psyche Mission. This was a lecture that was given just beforehand, or a few months beforehand, so you won't see the launch in this video. We may be able to show you something in one of the meetings next year. This lady, Professor Lindy Elkins-Tanton, is the principal investigator for Psyche, for that mission that you saw Dave got off the Earth and on its way. As usual, while this is going, feel free to get up quietly and go outside and have a cup of coffee and come back if you wish, or stay out there and have a chat. All of this will be online because it's being recorded anyway, so you can watch it at a later time on YouTube if you miss out on something.
There aren't many classes of objects left in our solar system that we haven't looked at up close with a spacecraft. And one of them that's left is the metal asteroids.
16 Psyche is an asteroid that orbits the sun out between Mars and Jupiter.
The reason that Psyche is unique is that it is metal rich. It's believed that it may be a remnant core of an early planetesimal that was formed in the very, very earliest parts of the formation of the solar system.
And after this planet started forming and this metal core formed inside of that, it collided with other bodies that then stripped off the rocky mantle, leaving this core in place.
This is the part of planets that we can't sample directly today.
It's too hot, the pressure's too high, our instruments would melt. Can't drill a hole that deep in the Earth or other planets. So how do we study the core of our planet?
Psyche gives us the opportunity to visit a core, the only way that humankind can ever do. And it would be the first metal object that humankind has ever visited.
We've been approved to go in August of 2022. It'll take a number of years to get there.
Flies past Mars, gives us a gravity assist, uses our propulsion system to then slowly creep up toward the end of 2025, getting there in early 2026.
We'll go into 4 concentrically smaller orbits to collect the necessary measurements that we need from our 3 primary instruments.
So our payload consists of a couple of imagers, which are cameras that take pictures of Psyche. Also a gamma ray neutron spectrometer, which allows us to measure the elemental composition of the surface of Psyche. And then a magnetometer, which will allow us to detect any magnetic field that's left at Psyche.
If Psyche still has some sort of remnant magnetic field, that probably tells us it really was a core. It's a strong indicator. We also use the radio on the spacecraft as an instrument, so we can map out the gravity and map out the interior structure that way.
We're using a particular thruster technology, Hall effect thruster technology. They operate 5 times more efficiently than normal rockets, so they use a lot less fuel, and is what allows us to get into orbit around this asteroid.
Solar electric propulsion has been around for quite a while, and it has flown before, but we're continuing to push the boundaries. We're going to have big 5-panel fold-out solar panels that will provide the electricity for the thrusters, which use as propellant the noble gas xenon.
This will be the first time that Hall effect thrusters have flown in deep space.
Studying the evolution of a planetary body is a detective story.
There's a magic to when you actually are on the launch pad and you say, we're go for launch.
And you feel like singing and dancing and you feel like throwing up at the same time.
Let's go discover things about our solar system that we have no other way to do. I think that it's fundamental to who we are and also who we should be. It's an incredible opportunity to be a part of the team making that happen.
All right, so that was very good to get that. Hang on, to get that up there. That was good to get that up there because they were going to have to do a condensed version, but now you kind of got the outline, right? So thanks very much for coming to the talk today. I really appreciate it. Very important caveat that I'm going to repeat through the talk. This is artwork done by fabulous Hollywood artist Peter Rubin, who's also done things like he designed one of the S's for Superman, and he worked on Ghostbusters. You get in the drift. This is art, right? This is not a picture. This is his interpretation of my description of what we imagine and hypothesize the science to be. We used to Zoom together on weekends for like a year while he did this art. Probably it's going to be totally different than everything I tell you today. And that's one of the things that's fun about it. All right, so as humans, we've sent people to rocky bodies like the moon and robots elsewhere. This is the Orientale Basin. It's a big impact basin on the limb of the moon. Chip, is this one of your favorite basins? I think it's so gorgeous. I think it's the best one. Here's Burns Cliff on Mars, another rocky body that we visited with robots and continue to visit. And we've been to great big ice and gas giants. This is Jupiter's great red spot, and then here's an icy moon. But what we have never done is visited a body that seems to have a metallic surface. And we think that Psyche has a metallic surface, as explained in that little trailer video. Again, this is just artwork, just artwork. But I think that is the most compelling thing about the whole deal, because there aren't many classes of objects that humans have never visited. And so we're going to discover something entirely new and surprising, because we discover totally new and surprising things that outdo our sense of curiosity no matter where we go in the solar system. And here we're going where all we have is wild guesses. All right, so what does it actually look like? Since I'm being clear with you that we don't know, that's what it actually looks like. That's what it looks like from my backyard. The red circle around the little asteroidal dot, which is just what those early discoverers were discovering. And we have no pictures of it, but we have shape models. So these shape models, and because we have astronomers here, I'm just going to add this. This is a figure from Shepard et al. 2021. And you can see there are 3 generations of shape models, 2 of which belong to Shepard, and then there's a third one. And he's pointing out that they are kind of in agreement. And they do it by looking at observations acquired at a wide range of wavelengths. Arecibo, S-band delayed Doppler imaging. Arecibo does not exist anymore. That's very sad. The Atacama Large Millimeter Array, plane of sky imaging, adaptive optics from Keck and the Very Large Telescope, and also stellar occultations where they watch the stars and the apparent path of the asteroid intersect. And so by looking at the way light and radar reflect off this spinning object, they can actually see how the reflected light in radar coming back changes, and knowing how fast it's spinning, they can make a shape model of the object. So this is the best that we know, but it's also misleading because there are other shape models done by also excellent groups that don't look like this. And so we think it's kind of a potato, but that also, potatoes can be lots of shapes, can't they? So here's one of our best shape models for Psyche on the left, and here's Vesta, recently visited by the Dawn mission. And then there's Eros, which I like to show, also visited by NASA missions. And Eros and Psyche, of course, are the mythological couple, which is kind of fun. There is also another asteroid that has recently been visited on the screen right now. I don't know if you can see it. It's right there. That's how big Bennu is in comparison to these others. I think a lot of us, including myself, tend to sort of think of asteroids like we are in Star Wars or Star Trek, and we can just like zoom in between the asteroids, and they're all more or less the same size and the same stuff. And so it's good just to remember that they represent the building blocks of the planets, and they're very different from one another, both in size and composition. So visiting a new one means discovering a whole new kind of world, really. All right, so recognize this beautiful relief map of where we are. I want to show you how big Psyche is. Psyche is this big. And so perhaps not giant compared to a state, but for an asteroid, it's very big. And even though there's well over 1 million asteroids known in the main belt of in the main asteroid belt, Psyche has something like 1% of the mass. So it's large and dense, large and dense. So what do we think it is, large and dense? I think this is the only data I'm showing. And I know that not everyone watching and listening today is a scientist, but I know that you hate to be condescended to no matter who you are. So let me walk you through this chart. I think it's super interesting. And it's the first way that we think about what Psyche's made of. All right, let's look at the vertical axis first. It's density in kilograms per cubic meter. And when you look at this density axis over here, you see that there are 3 red lines that intersect it. The top one says camosite. That's an iron nickel metal mineral that comes from meteorites that we think is most likely more or less the composition of the metal part of Psyche. You see, it's about 7,000, it's more than 7,000 kilograms per cubic meter in density. Next down is troilite, that's iron sulfide, which we also expect to find on Psyche. And then at the bottom, enstatite, which is a rock-forming silicate mineral like you might find in a rock outdoors. And so rock, this is what you should be taking home if this is not your world. Rock, about 3,000 kilograms per cubic meter. Metal, more than twice as dense. And so by plotting the densities of the asteroids, you can see at a glance probably how much metal or rock they might have in them. That might be an example of what we're fighting with the interference. So then the horizontal axis here is the year of publication of people's estimates of the density of Psyche. And my favorite data point, of course, is that one around the year 2000 at 11,000 kilograms per cubic meter, which if you are a scientist in this field, there's literally no material that could be. And so I've got to look back and see what they really thought it was. It would have been super exciting because it would have been actually a brand new kind of material. And then you could see how the density estimates kind of funneled down. And then we were selected for flight in here. And after that, people have been pretty clear that Psyche is around 4,000 kilograms per cubic meter. And so that would mean it's a mixture between rock and metal. But it's actually quite outstanding. Right at this moment, here are 4 other asteroids. Cleopatra is a metal asteroid. There's only about 9 asteroids that are thought to be made of metal. And so at the moment, you know, these things change as people get better data. At the moment, Psyche is the densest asteroid known. And most asteroids plot down here in this gray field, meaning that they are void space and ice and a little bit of rock. Psyche could be pure metal plus void space, you know, space fractures filled with the vacuum of space. Or it could be a mixture of rock and metal. Or it could be a mixture of something that's not rock, like carbon and metal. We don't know. But that's the first line of evidence that says Psyche has got a big metal component. All right. You who study meteorites are going to look at this and go, this is nuts. So one of the things we've tried to do is compare the spectra, the reflected light spectra off of Psyche, with the reflected light spectra off of meteorite samples. You may know that virtually all the meteorites we have on Earth are recent transients from the asteroid belt. They were knocked off of asteroids, except for the super special ones that came from Mars or the Moon. Almost all of them come right from the asteroid belt in fairly short order. So they're good examples. They're sort of a compositional library that we can use to compare to Psyche. Psyche's spectra matches meteoritic metal, like that camosite, and troilite. And it matches these bizarre meteorites called CB chondrites. And if you look at the one on the left, the gray is iron nickel metal. Don't they look like bubbles? Like they're all pretty round, right? So we think that they were liquid and they froze as droplets. And in between them is the darker material, which is silicate rock. And I'm going to mention this for those of you who are specialists because it's so interesting and strange. The spectra from Psyche indicates that the silicate rock component, or whatever is not metal on Psyche, has almost no iron oxide in it. This is a very rare thing. If you pick up a rock on Earth or Mars or Venus or the Moon or Mercury, you would find minerals in there that have both magnesium and iron oxide in them, and they have a very distinctive spectra. Psyche does not have that. And so that's an interesting thing about this meteorite, is that those rock bits between the metal spheres have very little iron oxide. So this is the kind of sleuthing we're doing from a distance to try to figure it out. So again, let me say, we do not know what it is. Does not really make sense for it to be a giant CB chondrite. So we'll find out. But this is basically how we think that planets are made in a super simplistic way. We start with a spinning disk of gas, dust, and pebbles over at the left. And then it used to be when I showed a slide like this, I had an asterisk right there between that and planetesimals. And I would say that's the international scientific symbol for "and then a miracle occurs." Because for a long time, people had no plausible physical way to get from dust and gas to these tiny planets, planetesimals, the size of continents or big cities or even maybe the size of the moon. There wasn't a plausible physical pathway. Now there's lots of good ways that people think it could happen. It's really kind of cool. So I took the asterisk out. So they clump together into what are called planetary embryos, things like the size of Mars, and then finally up into planets. And so we think that Psyche is a little part of one of those planetesimals. Maybe it got its rock knocked off, like we were talking about in the video. So the data right now says that it took only 5 million years to make Mars. And the number that I always joke, I used to tell my students they fail if they don't remember 4.568 billion years ago, because that's the age of the first pebbles that formed in our planet, in our disk. So like the first solids in our solar system, 4.568 billion years ago. Only 5 million years after that, we had Mars. Earth may have formed as fast or faster, but the giant impact that created our moon happened about 100 million years later. So if our solar system was 24 hours long instead of 4.568 billion, Mars was made in 94 seconds, and the planetesimals were made in 20 to 30 seconds. So they are remnants of the very earliest part of the solar system. So these are stills from that beautiful little video that was actually a flip book that we gave to our reviewers because we wanted them to understand our vision in our heads of the process of making Psyche. Because without knowing that little video that you just saw, where it goes like this, and then it goes like this, and then it goes like this, you wouldn't understand why we even chose the instruments that we did. So we made flip books for them, and Peter Rubin, again, did this artwork. So now we're imagining that Psyche is mostly a stripped metal core with just a little rock on the outside, and that its convecting interior metal is making a magnetic dynamo, the same way our Earth makes a magnetic dynamo. And we hope that maybe it happened this way, because if it did, then the metal on the outside is freezing into that lid while the inside is still making a dynamo, and that metal could hold onto the magnetic field for us to go and measure in 2029, which is the actual date that we're getting there. And you see this yellow squirting out. There's a wonderful process of core formation whereby the metal liquid immediately separates into two liquids like oil and vinegar, only it's not oil and vinegar. It's boiling hot liquid iron and iron and sulfur. And so that iron and sulfur immiscible liquid is buoyant and could squirt out. So these are hypotheses we've had for years. Who knows what we're going to see? I can only just pretty much say it won't be this, even though this is our best guess. So today it might look like this with just little regions of magnetic field, and our spacecraft will go around and go in and out of those magnetic field lines. We hope. Wouldn't that be great? But who knows? So where is Psyche? There are the asteroids in purple, and there's Psyche's orbit way in the outer main belt between Mars and Jupiter. How many of you have seen one of these fabulous headlines about how Psyche is the asteroid that's going to make everyone on Earth a billionaire? Did anybody see that? You've seen them. A couple of people have seen them. And I hope that you understand. So this was like really people got very excited. There have been literally hundreds and hundreds of these stories, including in Forbes magazine. And so, dare I tell you all the ways that this is wrong. And I'd like to talk about it here because look how far away this thing is. We're not even taking a sample ourselves. We have zero technology to bring this asteroid back to Earth. It probably would be a gigantic catastrophic error if we tried. And imagine that we did. Imagine we could bring Psyche back. Would it be worth anything? No, because talk about a surplus on the market. You would crash the whole metals market, and all of your work would be for naught. And so there are at least 15 ways in which this idea that this asteroid is worth all this money is a fallacy. But the guy who writes for the Space News on Forbes told me that he still likes to at least mention it while he disproves it because it gets so many people's attention. Put a $ in front of it, they're pretty excited. Anyway, Psyche's far away, you're not bringing it back. And it is never going to hit the Earth. It's not Earth crossing. So we've got 3 science goals. Understand previously unexplored building blocks of planetary formation, that is the iron bodies. Look inside terrestrial bodies by looking at cores, the only way we ever can. And explore a new kind of world. Just explore something new. What does a metal surface look like? We have no idea. Objective A, we have 5 science objectives. I know that you won't be surprised to know that NASA has a very highly structured way that you're meant to propose and carry out a mission. And one of the reasons for that is you want to have science goals that you can actually attain with the instruments that you're going to fly. You need to know what those questions are and be pretty sure that you know how to answer them. And so our first of our 5 big questions is determine whether Psyche is a core or is it something else. And so we write this as unmelted material because one idea would be maybe Psyche is material that formed very near the sun where it was extremely hot and irradiated, and that heat and irradiation reduced the iron oxide to iron metal in the materials of Psyche. I would argue, and maybe somebody can come up with a very unusual meteorite sample to prove me wrong. I'd argue that we have no samples of a material like this, but it's theoretically possible. And so this is just to say, this is the kind of world we're in, trying to figure out what Psyche is based on the data we have right now. Psyche itself is an improbable object. It's the largest of the very dense, apparently metal-bearing asteroids. And there's more data that I didn't show you, of course, but some of the data is contradictory. And so right at this moment, we really do not know what it is. And I think that's kind of great because it gives me this lovely luxury in science of having like no ego-born determination that I want to prove a certain thing to be right. Because I don't have a hypothesis about this to prove. We have lots of ideas about how to test these questions, but we're all going to find out together. So I'm reinforcing again that we don't know what it is. So how does a NASA mission happen? Well, for me, It started with this paper that I wrote with Ben Weiss, who's now the Deputy Principal Investigator of the mission, and Maria Zuber, who's the Vice President for Research at MIT, and is also the lead of our gravity science investigation on the mission. So we're all on it together. We wrote this paper back in 2011, and it was, does it sound like, for those of you who do not study meteorites, does this title, Chondrites as Samples of Differentiated Planetesimals, immediately cause a surge of rage and indignation in you? Does it fill you with like anger and a wish for retribution? Well, you're in the wrong field, because that's what happened to us. People thought this was a really horrible idea, and it was. I'd like to tell this story just because it super amused me and scared me at the time, and now it just amuses me. But I was junior faculty at LPSC when Ben gave his paired paper where he did the measurements of Allende. I'm not going to tell you the whole story; it takes too much time. And I gave the models. And it was at the Lunar Planetary Science Conference, and I'm getting up from my seat because I'm the next speaker. The room is totally filled for our talks, and like there's standing room only, there's people standing around the sides. And I'm walking up toward the podium, and before I even reach the podium, people are lined up at the microphones to rebut me. I hadn't even started talking yet. And so that was the only time in my life that ever happened. And it was kind of fun, and we all had great conversations, and some people agree with us and some people don't. But what happened was 2 guys from Jet Propulsion Laboratory, 2 scientists, wrote me an email and said, "We really liked your paper. Do you want to try to propose a space mission to test your hypothesis?" And that is how this started back in 2011. I was working at Carnegie Institution for Science at the time, and we started working on it, and it took us a little while to even decide where we wanted to go to test the formation of planetesimals. And after about 6 months, we decided it was Psyche. And then 3 years later, we handed in our step 1 proposal in the NASA proposal system. Now, I'm sure many of you know that NASA has many different sizes of missions that they fly in planetary science. The really big ones, like the Mars rovers and Europa Clipper, that kind of thing, those are called flagship missions. And they are conceived of and run, really managed out of headquarters. And then there are competed missions, of which there are a number of different classes. The one that we competed in is called Discovery Class, and those are led by scientists. They're led by principal investigators, which in this case was me. And so my job is to, get the mission manager, which in this case was JPL, and our industry partner, which ended up being Maxar, and then all the other partners around the world, and all the science team, and like trying to get everybody to work together to do this thing. So we wrote this 218-page step 1 proposal with about 40 people, and we competed against 27 other proposals. And to my undying astonishment, we were selected to go into step 2, cover art by Peter Rubin. Recognize what this is? This is the moment of impact between 2 planetesimals that might strip some of the rock off one of them. So we're always trying to tell our story, telling our story. Step 2 proposal, this is like 30 seconds later with the impactor screaming off to the side and some of the liquid iron metal core showing underneath the rock that's being stripped away. This was a 1,000-page proposal. That we wrote over the course of a year with a team of 150 people. And that's not even the only thing you do in that competition year. It really was insane, and I could talk to you about it at length if you want to hear all about like a thing that is like 7 times your PhD qualifying exam, enacted as a Hollywood super production. That's like what these site visits are like. And so one of the things that happens at the site visit is you get encrypted emails from the review board asking you questions about your mission proposal. And at first, David O., who you saw on the mission trailer, our lead systems engineer, he and I were like, oh my gosh, but then we have a whole week to answer them, no problem. And then I realized these are the questions from experts that were not answered in 1,500 pages of previous documentation. And in fact, we ended up actually doing new space physics during lunch break to answer questions that end up being published, like stuff like that. It was really intense, super fun. We were selected, oh my God. So that morning in January of 2017, I told this story in like a blog and things like that if you want to read about it. It was a kind of a funny moment getting a call from Thomas Zurbuchen saying we were selected. I had become completely sanguine through the great counseling efforts of my husband because I felt responsible for everybody, including, oh my gosh, the team at Maxar. They were trying to become a NASA prime contractor for the first time ever. All these people who'd spent so much time and money trying to make this happen. And I was just ready to hear no, and it was cool. And then we figured out if we were going to do it again. And he calls up and he goes, you're going to be glad I woke you up this morning, he said, because he knew right away I'd been asleep, which was embarrassing. And he said, we were selected for flight. But the very first thing he said was, I need you to completely redo your student collaborations. I want to do something much bolder with your mission. So we came back with 10 different ideas from a new, bolder version of student collaborations. So we ended up choosing 4. We do undergraduate, senior, capstone programs. University of New Mexico is not a capstone partner of the Psyche Mission, so I'm here to invite you to become a partner with us in capstones if you want. We get real problems from the mission, from members of the mission who want real things solved, and they go out to student teams, and we try to get the teams to be interdisciplinary, not like electrical engineers working with chemical engineers, because that's like not actually interdisciplinary, but to have a student project manager and somebody who does marketing and someone who does budgeting and someone who does UX, UI, and someone who does coding, and like everybody you actually need, like you'd work with in the real life to do this. We have free online courses, one on the evolution and timeline of a NASA mission, one on how to put together inclusive teams, taught by a super expert, not myself, on this topic. And we have one coming on the debugging mindset and another one on the small bodies in the solar system, free to everyone in the world. We have got this great art program. We do it competitively. Undergraduates in all American 2- and 4-year colleges in any major working in any media are welcome to propose every year, and we choose 16 artists and we fund them to produce original art. And it is so cool, and you can see it on our website, which is there, psyche.asu.edu. We get, graphical art. Someone was a jewelry maker. This guy was a ceramicist. You see that glaze? That glaze is a mixture of iron filings and thermite, which is an explosive. And he put it in his kiln, and it made this amazing texture. I learned about it afterwards, which was good. We've had cooks, like everybody, so you're welcome to join. We have had over 1,500 undergraduates in 6 years participate with us, including 1,300 in our capstone programs at 58 colleges and universities in 24 states and Puerto Rico. And I'm really proud of this program and really glad that NASA could fund us to do it, and it's just a joy every day. So, who are we? We are, as I was saying, ASU, JPL, Maxar is our industry partner. The Johns Hopkins Applied Physics Laboratory, led by David Lawrence, is making our gamma ray and neutron spectrometer. Malin Space Science Systems, ASU, led by Jim Bell, is running our imagers. And our magnetometers come from Danish Technical University. The gravity experiment relies just on Doppler radio with the high gain antenna. That's being led by Maria Zuber at MIT. This is a big project. And at peak, we've had 800 people on the team. Right now, I think it's a little bit hard to count because we have people in so many different places, and there are teams that, at APL, how many people are really counted as a part of the team and who is just, it's hard to count. But I think we're at about 350 people right now. And the total budget of the project is over $1 billion. And so there's a lot of pressure and a lot of responsibility to make this happen. There's our 3 instruments that I was just mentioning. There's actually 2 magnetometers and 2 imagers that you saw on the video, right? And the beautiful gamma ray and neutron spectrometer. And today, one of my great moments today was actually having Rich really explain to me how cosmic rays get to be as energetic as they are, because I've never understood that physics. But it's cosmic rays that hit the surface of poor, naked, airless Psyche and cause those atoms on the surface that are struck by the cosmic rays to release gamma rays, which we measure with our gamma ray spectrometer, that tell us the identity of that exact type of atom. That's how we get the composition of the surface. We get the composition because the body gets struck by cosmic rays that come from the shock waves in the front of supernova explosions in other galaxies. Isn't that cool? Does that not pull together these 2 departments? I think that's kind of great. So here's how big it is. It's a big spacecraft. You see we've got these booms up on the top, and we're actually lifting our instruments away from the main body of the spacecraft so that the spacecraft itself doesn't interfere with the measurements. And I've had people ask me, well, if you put your science instruments way on the outside, like what the heck is inside this giant box? You might not know that the Mars rovers, when they get packed into their boxes, their equipment is so tightly packed that you can't slip paper in between it. And we've got mostly space inside this box, electronics, and a giant tank of xenon. But the reason that it's bigger than we need it is because we bought a more or less off-the-shelf model from Maxar Technologies, because they built over 100 Earth-orbiting communication satellites that use exactly this power system. So that's why we chose them. They could give us a firm fixed price. They knew exactly what it was going to cost to build this thing, and they saved us a lot of money. And it doesn't really matter. We launched some extra space, empty space, into space. So the other thing I want to mention over here, DSOC, D-S-O-C, the Deep Space Optical Comm. That is a technology demonstration that we're flying on behalf of NASA to test the technology in space. This amazing, oh my gosh, if we have time and questions and you're interested, I could like geek out on the tech here. But what it's doing is communicating with Earth using lasers instead of radio waves. Turns out you can encode a lot more information in a laser than a radio wave. So we joke that in the future, this is how we're going to get Netflix on Mars. So as we're going, we'll be testing this, and you can watch, this is going to be tested as we're flying through our cruise. When we unfold those beautiful solar arrays about the size of a singles tennis court, and here at Earth, it's 20 kilowatts of electrical power. And then because flux is a 1 over r squared relationship, the further you go away from the sun, the flux goes down as 1 over the radius squared. And since Psyche is out at 3.2, 3.2 squared is kind of like 10. So at Psyche, you get 1 over 10, about 1/10 of the power that you would here at Earth. And so that's not much. You can either run a hairdryer or you can run our whole spacecraft. Propulsion, coal gas thrusters, all the instruments, the works. It's just amazing, amazing to design that. We are going to launch on a SpaceX Falcon Heavy. And so they're going to re-land the side boosters with the biggest sonic boom you'll ever hear in your life. Because I'm going to sit on console for that launch, and a bunch of us got to go and sit on console for the launch back in November. And as soon as the Falcon Heavy left the launch pad, we all ran out of mission control into the parking lot to watch the boosters land, like 3/4 of a mile away. And they came down through the morning fog bank. You couldn't see them at all. And suddenly you could see them. They get into the open air in the morning in Florida, just under the fog bank. And they snap on their engines so that they can slow down and land properly. And there's this vast sonic boom. And I actually shrieked a little bit, which isn't totally like me because it was just so loud. And one car alarm went off, and it was a Tesla. So I thought that was hilarious. I'm not even making that up. Yeah. But wait, as you heard in the video, we were supposed to launch in August last year. And by having this time curtailed, what you're actually being spared is like having me cry for a while because it was so hard to go through the slip. It is a huge deal to slip a mission. It's vastly expensive. And there has to be a long review with a big professional board who just grill you mercilessly to find out all the things that went wrong. We were a bit surprised. We did not know the thing that was going wrong until it was too late to fix it, even though the team is so awesome. But let me just say, a team that can build a complete, fully functional spacecraft and deliver it to Kennedy during COVID, 100% during COVID, they are miracle workers. And I support these people like to the ends of the earth. And the bit that didn't quite get finished was mostly in the software. But we continued to go through this exciting day called a continuation termination review, at the end of which everyone votes, continue or terminate. And you can imagine, been working on it for 12 years, expecting it to be the bigger part of my career, hundreds and hundreds and hundreds of people and a ton of money. There's a lot of pressure when that happens. And so last year was not the highlight of my life. I'm really kind of hoping this year's going to be a better year. The team's doing great. So we are now launching in October of 2023, October 5th. Please put it in your diary. And keep your fingers crossed, both hands from now till then. I don't care if it hurts. I need you to do this. I think we're going to make it. October 5th, 2023. Then we're going to zoom around and get a Mars Gravity Assist in May of 2026. And then finally, we're going to head out to Psyche capture in August of 2029. So yeah, I think that's it for that. So it's almost 6 years. It was going to be 3.4. Psyche's in a little more awkward place. But it turns out it's actually in a better place for science. Because an interesting thing about Psyche is that the Earth and the other planets, for the most part, our spin axis is perpendicular to the plane of our orbit, or kind of close, like tilted. Psyche's is knocked right over into the plane of orbit, so it's like a rotisserie chicken. So you could imagine that's just a good image. It totally brings it to mind what Psyche is, but like a rotisserie potato, maybe. So for a quarter of the year, its north pole faces the sun, and its south pole is freezing cold nonstop. And And then it gets kind of sideways to the sun, and the whole of Psyche is illuminated as it spins. Can you picture that? So we have better lighting conditions with this arrival. So it actually helps the science in that way. So as you saw in the video, we're going to step down, we're going to get all this data, we're going to get closer and closer as we better determine the gravity field and can calculate stable orbits as we go down. So a couple words about the importance of teams. Here I am with just a little part of our giant team. Something that has actually been the biggest driving force for me in my work is to try to find teams of people where the sum of the whole is bigger than the parts, where people are actually supporting each other to do better. And I think a lot of times in any high-stakes world, knowledge, money, whatever it is, you have people who kind of act like they own the city-state, and they're not always supportive of everybody, and it's easy to feel like you're being bullied out, or it's just not a supportive environment. We tried really hard not to make it that way. Not just because it is ethically the right thing to do, but because it's literally a way to buy down risk. Why positive team culture matters. You make better decisions. More ideas are heard, cooler heads think better. Project risk is thus reduced. If you can have everybody willing to speak up, we had this motto, best news is bad news brought early. And you can imagine how this kind of hurts me even to say it, because it didn't work, right? I would say 70–80% of the team, it really worked. The person with the authentic boots on the ground knowledge was the one who was asked to answer the question, not their manager's manager whose voice wanted to be heard. And when someone knew something was wrong, they knew that they would not be punished for telling that. That's what you need. You need the person with the soldering iron in their hand to say, I don't think this chip works. To have the courage and knowledge they'll be supported. Otherwise, you won't find out till after you launch. In a little part of the team, it didn't work, and it breaks my heart that that's true, but it's a big learning. Also, attraction and retention of talent. It turns out, however it is that you think of yourself, like however you identify yourself, if there's fewer than about 30% of people who are that same way in your group, you feel like you're alone. This is sociology science. And so if you do feel like you're alone, because you're in a group where there isn't a lot of you, it's much easier to feel vulnerable. If you don't feel like you're going to rise on your merits and be respected regardless of whatever it is that you look like or act like, you're going to feel vulnerable. So it doesn't matter what your hiring rubric looks like, you will not have a diverse team. So just trying really hard to make it possible for people to rise on their merits and for every voice to be heard, I think is a huge ethical and quality imperative. So I just had to proselytize for a minute. So let's see the spacecraft. So this is a spacecraft shipping container. For a big spacecraft. This is Maxar's one. I have a great story about the one that we subsequently bought that I'd be happy to tell you later. The spacecraft is held up in there, and it's actually a self-enclosed clean room, absolutely sealed, very low particulate, and it's instrumented to everything, to pressure and shock and acceleration and vibration and temperature, and it has 2 generators in case one fails, and that's how this thing gets trucked around. So that's and to my alarm, I was like telling this story. There's a stencil just past those guys on the shipping container that says, "Space flight hardware do not drop." Which I still wonder, like, how was it even possible to drop it? And how would you not know what it was? I don't know. So the spacecraft chassis arrives at JPL in March of 2021. Here they are in the one of the 2 giant high bay clean rooms at JPL. And just feeling so excited. This is me and Henry Stone, our project manager, feeling so proud that week because there's our spacecraft all ready to be assembled at JPL with all of the science instruments and the software and the computer brain and all the rest of it. And going into the clean room isn't something I indulge in very often because I'm not building the spacecraft and I just disturb people. So unless there's something I need to see or a tour, I don't go. But going in is also just a weird thrill. You have to put on all this special equipment, and you have to put an electrically conductive band and this wire, which you could see, I could see it in a subsequent thing, and you have to plug it into the wall and degauss yourself so you have no static electricity in your clothing. Then you go into a little thing the size of a phone booth that is just filled with air nozzles, and it blows air all over you and sucks it out the top to get any extra particles on you. It's called the air shower. And they at first I thought they were mocking me, but they instructed me to put my hands up and dance in a circle. And so 1 by 1 or 2 by 2, you go in the air shower and dance in a circle, and then it's like an incantation. Then you're allowed to see the spacecraft. So that's what that is. So here's the great team that just finished installing the Deep Space Optical Comm. Very excited about this laser comm. Here's a hero shot. That was supposed to be 1 year to launch, right? Didn't happen. Still a hero shot, kind of nice. There's the gamma ray and the neutron spectrometer. And, oh gosh, so these are the thrusters. So 2 thrusters per arm. The arm has like a shoulder and an elbow so that they can be moved in the right location. And by the way, the video has it wrong. There are 4 thrusters, but only 1 will ever be on at a time. So we're kind of working with them to fix that, but it's kind of an expensive fix to fix the thrusters. And there it is installed on the left. And then here's what it looks like when it's actually working in a thermal vacuum chamber, this one at JPL. No, actually, I think this was at Glenn Research. We tested them in both places. So it turns out ionized xenon is blue, and so that is what it's going to look like. It's going to look very Star Wars as we go through space, running on noble gas. You have to test that there's no electrical or magnetic interference and the compatibility of all the systems going on. But to do that, you have to put the spacecraft into a Faraday cage that excludes all the external magnetic and electric fields. So what's a Faraday cage the right size for a spacecraft? Well, it's a huge tent of conductive carbon fiber or fabric. So that's our Faraday cage, and that's our spacecraft, and it went in for its testing, which it passed with flying colors. You also have to put it into a thermal vacuum chamber and test the thermal design at space temperature under vacuum. And for that, you need a big honkin' thermal vacuum chamber. See the people? The guy down on the left and the guy up on the left? And that's the bottom of our spacecraft with the adapter ring there, the gold thing. That's how it connects onto both the holder in the shipping container and also the rocket eventually. So that's how you hold it. So we're sliding it in there. This thermal vacuum chamber has a diameter of 25 feet. And to bring it down, they could bring it down to vacuum, the whole thing, after they bolt this giant door in place, and then make it really cold with liquid nitrogen. And it uses so much liquid nitrogen that on the days we were running it, there would be tanker trucks just lined up at the gate of JPL rolling in like one after the other, which was just I don't know, I love that stuff. It just kind of makes it all exciting. And this also has the ability to put solar on the top of the spacecraft so you can test your spacecraft when it's being baked from the sun on one side and frozen on the other side. Very complicated thermal problem. All of you who do thermal modeling and finite elements, you are needed in aerospace. Here you all saw that in the video, the beautiful wing. And here it is arriving at Kennedy Space Center last summer on a C-17. And that is not the Maxar shipping container. That's the one that we bought for this and 2 other missions. And they had to take it on a test run down at March Air Force Base in California to make sure it fit, because it's designed to fit with just inches on the side. Because the Maxar shipping container actually doesn't fit in a C-17, and a C-17 is the biggest transport plane that the government had to offer us. And so that was an exciting moment that it all fit, and it arrived beautifully, and it's still there. So my final slide here is me on the left. You can see my degaussing wire there. And Brian Bone, our assembly, test, and launch operations manager, on the right under the spacecraft, and he's pointing out with his flashlight the newly installed comms panel on that particular day. So I invite you to follow us on social media and look on our website, and keep your fingers crossed and join us for launch in October. Thanks very much. I'm so happy to answer questions, but I don't know what our timing is.
I think we have a few minutes.
Few minutes? Okay. And of course, if you need to go, please don't feel embarrassed. Any questions at all? Yeah. What are some of the obstacles we are anticipating after launch? Oh my gosh. Okay. The obstacles I fear the most, of course, are the unknown unknowns, because anything could happen at any time. One of the exciting things that happens after launch is there is a 110-day initial checkout, where we're going to test everything that we need to do with the spacecraft in preparation for proper thrusting on our trajectory. So, for example, these missions, the Hall thruster missions, are very different than chemical propulsion. The thruster is on almost all the time, but you always have to check and make sure you actually know where the spacecraft is. So we'll thrust for 7 days at a time, or 6, and then we'll turn it off, swivel it around, and communicate back with Earth, with the Deep Space Network, and say, am I where I think I should be? And how is everything? And then we'll turn it back around and thrust some more. And so I think one of the big obstacles is getting through initial checkout and testing everything that we need to test. During cruise, I'm feeling really good about it. And at arrival, I mean, what are the obstacles? Like getting over your emotional state, I think, is a part of it. But an interesting obstacle, and you can kind of think about this, any of you who are in a field like this, how do you design a mission to answer questions about an unknown body? What is the whole range of things that Psyche could be, permissible by the data that we believe, that would still allow us to answer our questions given the instruments that we have? And so we've tried really hard we have all these matrices and cartoon pictures and like stories and hypotheses that we think we're going to be okay. But one of the things I'm worried about is that it just ends up being quite different than what we thought, and we get measurements that we can't quite reconcile into answers for the questions we're supposed to answer. But I suppose that's kind of a wussy answer, because in a way that would be fabulous, but it would not be fulfilling what we promised to NASA. So it becomes an obstacle also. Yeah. Yeah.
I'm just wondering what happens to Psyche after it's done.
Yeah, I know. There will be what's called a senior review after we complete. Let us just use the definitive verb tense. There will be a senior review once we complete all of the science that we promised to do, and we will propose to do an extended mission, which would be to cycle down closer and closer to the body and get better and better data. There's no other asteroid going to be near enough us to go visit for any good reason, believe it or not. Like, they're just so far apart. And so some of the student artists on our program thought that was super sad, that this spacecraft that we loved and had nurtured and brought up wasn't coming home. So they made a children's book that's available online about how the spacecraft ends up coming down to the surface of the asteroid, and it's so happy because that's where it wants to spend the rest of eternity. But the truth is, it'll actually, like, unless we actually crash it, it would just be in that final orbit for hundreds of years before it goes unstable on its own, but it'll end up on Psyche. Yeah. Henry, did you have a question?
Yeah. Thinking about the science for a minute, do you have expectations that you'll be able to infer things like original size if this turns out to actually be a core?
Okay.
And what data might you and other collaborators bring to bear on trying to figure that out? Because I love the idea that it's a core.
Yeah.
I really hope it is.
Yeah.
I'll
repeat the question.
Reimagine,
Yeah. Right. So the question is, would we be able to figure out how big the original body was if Psyche is a partially revealed core? And Penny's saying that she loves the idea that it's a core and she wants to be able to imagine what the parent body was. Probably not. So here's the tricky bit. We puny humans have not actually witnessed giant impacts between planetesimals. We've seen the comet go into Jupiter, kind of a different deal. And so we have all these simulations, and we think we are beginning to understand how the rock could be knocked off of a core. But say Psyche started out like the size of Vesta, because it's sort of the size of Vesta's core. Eric Asfog at University of Arizona says it would take, his numbers vary depending on the model, but let's say between 5 and 11 oblique hit-and-run hits onto that original parent body to knock off the rock without completely destroying the center part. And that in between there can't be any strikes that really add material. They can't be accumulative strikes. They have to be just destructive strikes. Seems unlikely, right? Another way to do it is to have something kind of the size of the moon hit something sort of the size of Mars, and then the thing that's the moon can actually have its exterior stripped off it as it goes through a strike. And so maybe Psyche, if it's a core, is part of the core of a little planetesimal the size of Vesta. Maybe it's the part of a core of something the size of the moon. Maybe it's a piece of splash off a giant impact onto something the size of Mars. I'm actually not confident we will be able to tell the difference between those states, which is frustrating. But maybe we'll be surprised and something will happen. So this is, like, for all of us scientists, a kind of a cautionary tale. You can't use Occam's razor when you don't have many instances, when it is already a super outlier, not a part of a population, not in a normal distribution. It's an unusual object, and it might have a quite improbable story behind it. Yeah?
I heard an interesting idea that all of the isotopic similarities between the Earth and the Moon could be reconciled if the impactor to the Earth was itself a core and had no silicate mantle. Would it be possible to make a large body, a Mars-sized body where you had knocked off the mantle, or is that
That's an amazing idea. So the science that Zach is bringing up is that the isotopic similarities between the Earth and the Moon are quite unbelievable. Like, they seem to be exactly the same material. But the models that say something the size of, make up your body, Mars or whatever, hit the proto-Earth and spewed off material that became the Moon, but the models say that that material would preferentially come from, I believe, the impactor, is that right? Not from the proto-Earth. Therefore, it should have a different isotopic composition than the proto-Earth. Following? So the fact that it doesn't, the fact that it's the same, makes you wonder, how could this happen? So one idea was maybe the impactor didn't have any silicate rock, it was just metal. Maybe it was a fully stripped metal core. Could you make a fully stripped metal core as big as it would need to do this thing? And I would want to, get Eric Asfog to, he's the Mr. Modeler of this process. So I can't give you a definitive answer except to say he's been working on these kinds of ways to strip the rock off the metal now for years and years and years, and none of them are simple. And so I think it would be very hard and maybe impossible. Yeah. But just to add to that, he sometimes has done kind of Monte Carlo series of simulations of creating the solar system through impacts. And in many of them, there is no body like Psyche that results. And in some of them, there's one Psyche, and every once in a while, there's two Psyches. So it's an improbable object. Yeah?
Would you have ways to measure the interior composition or properties of Psyche?
The interior composition and properties of Psyche. Yeah, so the main way that we're going to do that is through our gravity experiment. And so this is done through Doppler. The idea that if something accelerates toward you, the waves are compressed, and if it accelerates away, they are expanded. You can literally do that from Earth using the Deep Space Network and the high-gain antenna on Psyche. So as Psyche is orbiting around, Psyche, the spacecraft, is orbiting around the asteroid, if there's a denser, like say an all-metal part coming up, the spacecraft will be accelerated toward it a little bit, and we'll have a Doppler signal to Earth. And then when it passes it, it'll be decelerated a little bit. And that's the way we build up the gravity field. We're going to get to degree in order 10. And so that combined with topography and composition on the surface, I think we're going to be able to infer something about the interior. You might be interested, in moment of inertia factor, if you're that kind of person. And I would really love to have moment of inertia factor, but I don't think that's going to happen. It's not processing fast enough, and it's too weird a shape, and so we're not going to get that. Anybody else? Oh, thank you. Hello, sorry.
My question is about visible light cameras. Will there be any?
Yeah, the imagers are visible light cameras. Yeah. They're, we call them imagers because it's fancy, right? Also because they're multispectral. Each one has a filter wheel with a set of filters that are designed to look at visible light or NIR spectral ranges that would help us identify certain minerals. And so, but we'll be able to put back together a faux color picture as well. And we've already built the software pipeline such that the images we get down off the Deep Space Network, we're going to put onto the internet free to everyone in the world within a half hour of our receipt. So everyone can see them. You can see the glitches and the things that look like rabbits and everything all at the same time. Yeah. Thank you very much. Oh, one more question.
Maybe it's a political question, but I couldn't understand the physics potential or science potential. Why we need to do this.
So your question is, why would we need to do this project?
My understanding is there are lots of astrophysical bodies that are roaming around in space. So, what kind of benefits or what kind of new thing that we are trying to extract from this object? Because we are investing lots of money in it.
Right, so the question is, why are we going to this object? There's lots of things out there to look at, and it's very expensive. So I have an approximately 5-hour lecture on this topic, but I'll just say, I have a couple of things to say. I think humans, in fact, it's more than I think, I'm convinced that humans explore because we can't help ourselves. We are going to space, whether people want to go to space, everyone wants to go to space, or everyone does not want to go to space. We are going to space. People are going to space. And it's going to happen on government money and private money, as in robotically. And with humans, I think we can't resist. And I think it is a fundamental part of the human soul. And I know it sounds hyperbolic, but I actually do really mean this. to look out over the horizon and find out about things. And I feel like if everybody had that thrill of looking and finding, we would actually be a better society overall. I think if everyone felt they had a sense of agency to go after an unsolved problem, that we would do better. And to see the things that we can do in space inspires us to do better on Earth, and not just in a hypothetical or abstract way, but literally with the technology comes right back to Earth to help, and that is not a stretch. And so there are many of these different reasons why I think robotic space exploration is very important for humans to stay humans. And then to go and say, like, why this body? Because there isn't another one like it. Because it's a new kind of object, because I think it's even more inspiring in curiosity. And I look at the interest. So this is a big, expensive mission, 100%. And I feel the weight and the responsibility of every taxpayer dollar 1,000 times. I really do. But we spend way, way, way more money, many multiples of this, on many other expeditions going to many other places. But I would say that this mission has gotten a lot of attention in the public because it's so new and different. And I think that is a benefit to all of us around the world, to think about something new and different and think about what's positive and practical in this sense, because almost every narrative we have in front of us today is a narrative of guilt and fear. And if we have a society-wide narrative of hope and excitement, I think that's worth everything. Thank you. It's such a mysterious object you have here. Hey, thank you. How are you guys?
Our world and beyond. Space, in partnership with the European Space Agency.
Gravity is one of the fundamental forces of nature. Its invisible grip governing our planet, from the rocks inside to the seas on the surface. And that makes it a vital reference point.
Gravity gives you the feeling of downwards. So what you call down is surely the direction of gravity.
We feel gravity as a constant pull, but add in extra mass in one spot or take it away, and the gravity signal alters a small but measurable amount. It's a puzzle for science.
Since more than 10 years, I would say since 20 years, scientists were dreaming of having a mission which gives us a high-resolution gravity field.
Gravity can vary in different ways. It can vary over time because of movements in mass, and it can vary from place to place.
In reality, we have different densities, different material in our planet, which is reflected by dips and bumps in the gravity signal.
In fact, if you look at Earth with the gravity scanning eyes of a satellite, it looks a very strange shape indeed. "300 years after Isaac Newton observed an apple fall from a tree, the students near Trieste in northern Italy are getting to grips with gravity. This is a fascinating starting point because beneath the ground is a huge cave called the Grotta Gigante. The cave's presence means the force of gravity here is slightly reduced.
The Grotta Gigante cave is a mass loss because it's a big hole in below our feet, and this gives us a nice gravity signal.
Less rock beneath your feet means less attraction towards the Earth. But the cave isn't the only factor in the local gravity field.
We have made 3 measurements in half an hour, And the student asked, yeah, but why do I see a gravity change? I'm sitting in the same place. So the answer is it's changing because we have earth tides. So the action of moon and sun changes the gravity field, and the earth responds elastically to the changes in gravity and deforms.
The best way to get a global picture of the gravity field is to go to space, and ESA's Goche mission does just that. Developing this unique global picture offers geologists an unprecedented view inside our planet. By studying Goche's gravity data, experts like Carla Breitenberg can track the structure and history of Earth.
This is a sedimentary rock, is a fossil included. This has smaller density. If we take a magmatic rock, this is a basalt, you feel it's much heavier. And this is typical of a volcanic environment. The third rock, which I brought, is a metamorphic rock. That means one or the other has been brought to very high temperature and pressure. The rock got cooked, and you get an even higher density. And this kind of rock type we want to detect by looking at the Goche measurements.
That gravity information can lead geologists to valuable materials like iron ore. It can also reveal how the roots of mountain ranges reach deep into the crust.
The crustal thickness variation is by about 7 kilometers in the ocean. They're the thinnest to about 75 kilometers over high mountains like Andes and Tibet.
Measuring the force of gravity can also tell us a great deal about the oceans. The waters of the seas are attracted by gravity towards concentrations of mass in the Earth's crust. Those same waters are also moved around by currents and tides. The goal is to understand the relationship between those two.
The mass distribution in our Earth, which determines our gravity field, is constant compared to the time an ocean current moves. So constant means over many years, over many decades, 100 years, 1,000 years. Whereas ocean currents flow, and if we know, as I said already, the gravity field, then we can see the effect of the ocean currents, which is about 40 to 80 centimeters on top of the gravity undulations. And this we want to measure. This the oceanographers need for the climate models.
The streams of data on the gravity field from the Goche satellite land here at the European Space Agency's Esrin base near Rome. The team that handles that information are aiming to make even better data available to the scientific community, and that means flying low.
We are currently in a phase of lowering the Goche orbit to bring it as close as possible to the Earth's surface, and thus to increase the sensitivity of the instrument for the Earth's gravitational field.
Goche has always flown far lower than other satellites, but now it's dipping down to an altitude of just 237 kilometers. At that height, the satellite is bumping along the outer edge of our atmosphere.
It can get quite wild depending on the sun activity, but at that low altitude, air drag becomes an important player for what concerns, let's say, the influence on the satellite's orbit. So that's why we have an ion drive on board Goche, which compensates the air drag that is impacting on the satellite.
One of the ultimate goals of Goche is to improve our knowledge of the geoid, a kind of gravity map of the planet. That strange, misshapen and theoretical view of Earth has long been studied here at Potsdam, home to the GFZ German Research Centre for Geosciences. Since 1995, scientists here have sent satellites into space to measure gravity. But way back in 1892, they were watching the gravity field here using a very precise pendulum in a room with a heated floor and temperature controlling valves.
The story is that we have a pendulum which is swinging roughly with a period of 1 second and a length of 1 meter in a vacuum chamber, and you can derive from the length and from the swing period the value of gravity very, very precisely. And that was the reference value which we used for nearly 70 years in the last century. Nowadays, we are using satellite systems like the GRACE mission. GRACE stands for Gravity Recovery and Climate Experiment, and what we are observing are tiny changes of the distance between the two satellites, while the first satellite is pulled to a mass in the system Earth, while the second satellite does not observe that at this moment.
The pair of GRACE satellites don't have the high precision of other missions, but they do offer something unique, and that's a monthly survey of the gravity field. Ingo Sasken has been using that temporal data to track the loss of ice mass over Greenland in the past decade.
You can see two things. So one thing is that you can see a seasonal cycle, but you can also see within the period of nearly 10 years, the bluish colors start to dominate, which means that the ice sheet has much less mass than we had before. Gravity is a very accurate and very true recorder of the mass change. And I think if you see these images here, there's no doubt that Greenland ice sheet loses mass, and we can accurately quantify it.
So, measuring the direction and force of the Earth's gravity field from space can allow us to follow not only changes in climate, but also see deep down through the crust into the mantle.
The big innovation of GOTSE is that for the first time we can have a global field which has the precision and resolution which is good enough to see mass changes which are related to geological structure.
Tracking the geoid, that gravity map of the planet, is also crucial for untangling complex questions in surveying and navigation.
That is very important because this surface is our reference surface which defines us. What is top, what is bottom, what is the reference for defining heights. For example, if you want to know the height of the Himalayan, you measure the distance between the mean sea surface level and the mountains.
All branches of Earth science have a healthy appetite for gravity information.
There's never an end in science. So, of course, we look ahead. We also discuss, for example, with our NASA colleagues whether we make a joint mission, because also NASA is working on the gravity field to determine the ice mass at the poles very accurately, and we are discussing whether we make a joint mission which takes the best of the two concepts to improve the gravity field further in the future.
Gravity will eventually be the downfall of GOTSE as its orbit is left to decay at the end of its mission and it re-enters the atmosphere. Its legacy is an unprecedented global survey of gravity's grip on Earth.
And with that, we'll close the meeting and we'll see you at the next meeting, which is January next year. Yeah, absolutely. We'll see everyone at the Christmas party.
Yeah, but why doesn't it work?
Oh, well, they don't say why.